There is a moment, if you have ever stood far enough from city lights, when the sky stops being a backdrop and becomes a place. It happens gradually. First, you notice the brightest stars. Then the dimmer ones fill in behind them, and then the ones behind those, until the darkness between the points of light is no longer darkness at all, but a kind of luminous dust, a pale river arching from one horizon to the other, wider in the south, thicker toward certain directions, thinning and fraying at the edges, until it dissolves into the surrounding black. You are looking at the Milky Way, and you are not looking up at it. That is the important thing to understand from the very beginning. You are not looking up. You are looking across. You are embedded in it. You are inside it. The band overhead is the disk of our galaxy seen edge-on from a position roughly 2/3 of the way out from its center. And what you are experiencing in that field, on that night, with the cold settling into your clothes, and the silence pressing in from all directions, is the closest a human being can get, with unaided eyes, to perceiving the true structure of the place where our species was born. Let that image stay for a moment. Let the scale of it settle. The Milky Way is, by any reasonable standard of the word, enormous. Its disk spans approximately 100,000 light-years from edge to edge. Though more precise recent surveys, particularly data from the Gaia Space Observatory, have revised that figure upward, suggesting a diameter closer to 120,000 light-years, and some structural features of the outer disk may extend even further. A light-year is the distance light travels in a single year, about 9.46 trillion kilometers, a figure that already exceeds comfortable human comprehension. Multiply that by 100,000, and you have a structure so wide that if you were somehow able to board a spacecraft capable of moving at the speed of light, the fastest that any object or signal can travel, according to everything we currently understand about physics, and you aimed it at the opposite edge of the galaxy, you would be traveling for 100,000 years before you arrived. The civilizations that built the first cities on this planet did so roughly 6,000 years ago. Anatomically modern humans have existed for perhaps 300,000 years. A light-speed crossing of our own galaxy would take 1/3 of that entire span of human existence. It would take longer than our species has been on Earth. The disk of the galaxy is not flat in the way a coin is flat. It has thickness, perhaps 1,000 light-years in the region we inhabit, thickening toward the center, warping and flaring at the outer edges, in ways that suggest ancient gravitational interactions with smaller companion galaxies. The Magellanic Clouds pulling on the disk's rim like a hand pressing on the edge of a spinning plate. Nested inside the disk is a structure of spiral arms: the Perseus arm, the Sagittarius arm, the Scutum Centaurus arm, the Norma arm, and our own local address, a smaller spur called the Orion arm, or sometimes the local arm, a modest offshoot between two of the major spirals, roughly 3,500 light-years wide, and perhaps 10,000 light-years long. The Sun sits in this spur, about 26,000 light-years from the galactic center, more than halfway out from the core, in a relatively quiet neighborhood. Circling the central mass at roughly 220 kilometers per second, and completing one full orbit every 225 to 250 million years. At the center of the galaxy, something is waiting. It does not announce itself visibly. It is shrouded behind tens of thousands of light-years of gas and dust that block visible light completely, which is why astronomers had to work with radio waves, infrared, and X-ray observations to see it at all. What they found, gradually, and then with startling confirmation, is a supermassive black hole of approximately 4 million solar masses, designated Sagittarius A star, sitting at the rotational center of everything you see. When you look up at that pale band in the sky, 4 million times the mass of our Sun, compressed into a region smaller than the distance from the Sun to Mercury. It is not active in the way the cores of some other galaxies are. It is not currently consuming material in vast quantities and blasting jets of energy across thousands of light-years. It is, relatively speaking, quiet, but it is there, and the entire galaxy, every one of the estimated 200 to 400 billion stars within it, plus the vast quantities of gas and dust still forming new stars, plus the stellar remnants, and rogue planets, and ancient globular clusters orbiting in the halo above and below the disk. All of it moves in relation to that central mass, 200 to 400 billion stars. That range exists because counting individual stars in our own galaxy is, paradoxically, harder than measuring distant ones. The dust and gas that blocks our view of the center also obscures large portions of the disk. We estimate using brightness profiles, stellar mass distributions, and comparisons with external galaxies, whose stellar populations we can measure more directly. The true number is genuinely uncertain. By a factor of nearly 2. We know our own galaxy less precisely than we know some things about objects millions of light-years away. All of this, the disk, the arms, the central black hole, the halo of older stars and dark matter extending beyond the visible edge like an invisible scaffold, constitutes the Milky Way. And the Milky Way is, in the context of galaxies, not small. It sits comfortably in the upper tier by mass and diameter. The Andromeda Galaxy, our nearest large neighbor, is somewhat larger in disk extent, but may be less massive overall. The Large Magellanic Cloud, one of our satellite galaxies, visible from the southern hemisphere as a detached smear of light, is perhaps 1/10 the diameter of our disk. There are dwarf galaxies orbiting the Milky Way: Canis Major Dwarf, Sagittarius Dwarf, a retinue of small companions that are so much smaller as to be difficult to compare meaningfully. In the local neighborhood, the Milky Way is one of the 2 dominant structures. So the picture so far is one of comprehensible grandeur. A galaxy 100,000 light-years wide, a few 100 billion stars, a supermassive black hole at the center, a position in a local group of perhaps 54 galaxies. The whole group gravitationally bound and drifting together through larger-scale structure. This is the picture as it exists in almost every popular account of cosmology. Settled, measurable, enormous, but fixed. A number you can hold still long enough to examine. And now, consider what the title of this documentary is actually asking. How big is our galaxy compared to the universe? You already know the galaxy's size. It is the denominator you've just spent time with. So the comparison should be simple arithmetic. Take the size of the universe. Divide. Express the ratio. Done. The observable universe has a radius of approximately 46 billion light-years, giving it a diameter of roughly 93 billion light-years. That figure comes from a careful accounting of how far light has had time to travel since the Big Bang, 13.8 billion years ago. Combined with the fact that space itself has been expanding during that entire period, carrying distant objects further away, while their light was in transit. So the observable universe is not 27.6 billion light-years across, which is simply twice the age of the universe in light-years. It is 93 billion light-years across because of that expansion, and the mathematics of calculating it require general relativity, and the measured expansion rate, the Hubble constant, applied across cosmic time. 93 billion light-years divided by 100,000 light-years. The Milky Way is roughly 0.1% of the observable universe in diameter, in terms of volume. The ratio is more extreme. The observable universe is approximately 10 trillion times larger by volume than the disk of our galaxy. The Milky Way, all 100,000 light-years of it, all 400 billion stars of it. The entire structure that contains everything you have ever seen in the night sky, and everything your unaided eye could ever detect. That entire thing fits inside the observable universe roughly 10 trillion times over. If the observable universe were the Pacific Ocean, our galaxy would be a bathtub. A generous bathtub. But a bathtub, there is your comparison. The one the title promised. And it is staggering. Genuinely. The kind of number that functions as a perceptual reset. A moment where the scale of your own existence collapses into something almost comically insignificant. But here is what should have already caught your attention. Look back at that number. 93 billion light-years. Look at what is embedded in it, like a splinter you weren't supposed to notice. The observable universe. Why observable? Why that qualifier? Why not just the universe? You may have encountered this word before and treated it as a technical nicety, a scientist's way of being careful, the kind of verbal hedging that professionals use to be precise. But that doesn't really change the substance of what's being said. The observable universe is the universe we can see, and the universe we can see is the universe. More or less. Right? No. That word is not a hedge. It is a confession. It is the scientific community's formal acknowledgement that the universe extends, almost certainly extends, beyond the boundary of what we can observe, and that the size of that extension is unknown, not slightly unknown, not uncertain within a comfortable margin of error, not a detail that will be cleared up when the next generation of telescopes comes online. Unknown in a way that encompasses not just, we haven't measured it yet, but potentially, we cannot ever measure it in principle by any means, using any instrument that the laws of physics would permit to exist. The observable universe is not the universe. It is the universe as seen from here. Now, given that light moves at a finite speed, and the universe has only been in a state where light can travel freely for about 13.8 billion years, it is the sphere within which information, in any form, could possibly have reached us. Beyond that sphere, there is more, almost certainly more, possibly vastly more, conceivably infinitely more. And we have no direct evidence about any of it. Not one photon from beyond the cosmic horizon has ever reached us, because not one photon from beyond that distance has had enough time to get here, and because the expansion of space is actively pushing that boundary's contents away from us, faster than light. So when you divide the Milky Way by the observable universe and get your ratio of 10 trillion, you are comparing a known, measured, physically real structure, the galaxy you live in, to a boundary, not to the universe, to the edge of your view. The comparison is not galaxy versus universe. The comparison is galaxy versus the furthest thing you can see. And if the thing you cannot see is larger, how much larger? By what factor? By any factor at all. If the true universe is 10 times larger than the observable portion, the ratio changes. If it is 1,000 times larger, the ratio changes more dramatically. If inflation theory is correct about what it implies for the universe's total extent, and we will reach this, then the true universe may be incomprehensibly larger than the observable portion, and the ratio becomes a number with no stable meaning, a fraction whose denominator is either unknown or genuinely undefined. The question the title is asking has a clean, satisfying, quotable answer. 10 trillion to 1 in volume, and that answer is real and worth understanding. But underneath it, hidden inside the word observable, is a different and much stranger question that the clean answer quietly refuses to address. How big is the universe? Not how far can we see. Not how large is our information horizon. Not what is the diameter of the sphere within which physics has had time to deliver messages to our telescopes. How big is the actual, total, complete universe? The thing that exists, regardless of whether we can observe it. The thing that was born in the Big Bang, and expanded, and cooled, and filled with structure. The thing the Milky Way is genuinely part of. Not just apparently part of, because it's the only part we can detect. That question does not have an answer. Not yet. Possibly not ever. And the reason it doesn't have an answer, the reason it may be structurally impossible to answer using any observation from inside it, is not a failure of technology or ambition. It is a consequence of the most fundamental features of how space, time, light, and expansion interact. To understand why, you would have to understand what the cosmic horizon actually is, where it comes from, what it means for the relationship between an observer and the universe they are embedded in, and most importantly, what assumption is hiding inside the way we casually use the word universe, as if it referred to a single, bounded, measurable object with a well-defined size. Stand under that sky again. The Milky Way arches overhead, 100,000 light-years from edge to edge, and you are inside it, standing on a small planet in a quiet spiral arm, looking outward through the disk, at structures 10 trillion times larger than the one containing you. The scale is real. The awe is earned. But the certainty that you are comparing two known quantities, that our galaxy has a size, and the universe has a size, and the ratio of those two things is something we can simply calculate. that certainty is not real. It is the first thing that needs to go. To understand what the cosmic horizon actually is, you need to go back to a moment roughly 380,000 years after the Big Bang, not to the Big Bang itself. That comes later in this story, and it brings its own complications. Start here instead, at 380,000 years, because this is the moment that defines everything you can possibly know about the universe from your position inside it. Before this moment, the universe was a plasma, a hot, dense, opaque fog of protons and electrons, so energetic that photons couldn't travel more than a tiny distance before being absorbed and re-emitted. Absorbed and re-emitted, ricocheting endlessly through a medium that was, from the perspective of light, completely impenetrable. The universe was bright, everywhere, and visible, nowhere. There was light in every direction, and nothing that could be seen. Then, at 380,000 years, the universe cooled to roughly 3,000 degrees Kelvin, hot by any everyday standard, but cool enough for protons and electrons to combine into neutral hydrogen atoms for the first time. And when they did, the universe became transparent, in almost an instant on cosmological timescales. Photons that had been trapped in that scattering fog were suddenly free to travel. They streamed outward in every direction, from every point in space, carrying with them the thermal signature of that moment. A snapshot of the universe at 380,000 years, encoded in light. Those photons are still traveling. They have been traveling for 13.8 billion years. The ones that originated in the region of the early universe, that happened to be in the right position, at the right distance, to reach Earth at this particular moment in cosmic history. Those are the photons that our instruments detect as the cosmic microwave background, the CMB. The CMB is not a wall. It is not a boundary in space. It is a boundary in time, the furthest back in cosmic history that any electromagnetic signal can carry information, because before that moment, light couldn't travel freely, and therefore couldn't carry information at all. Every direction you point a sensitive enough microwave detector, you see the same thing, the thermal afterglow of that moment of transparency. Redshifted by 13.8 billion years of cosmic expansion, from 3,000 degrees to about 2.725 degrees Kelvin, just barely above absolute zero. That surface of last scattering, as cosmologists call it, is the wall at the back of the observable universe. Everything between here and there, every galaxy, every quasar, every filament of large-scale structure emits or reflects light that, given enough time, can in principle reach us. Everything beyond it cannot send us any electromagnetic signal, because before it, the universe was opaque. And even if we are patient enough to wait for light from the most distant visible objects to travel their full journey, 380,000 years is where the electromagnetic record stops. So here is the cosmic horizon in its most basic form, a sphere, centered on us, whose radius is the distance light has been able to travel since the universe became transparent. Beyond that sphere, we cannot see. The universe might continue, almost certainly continues, but it is beyond our observational reach. in the electromagnetic sense. Simple enough. And you might stop there and feel that the concept is settled. The universe is opaque beyond a certain distance. So our observable universe is a sphere defined by that opacity and the age of the universe. That is true, and it is important, and it is not the whole story. Here is where the hidden assumption enters. When you hear that the observable universe has a radius of 46 billion light-years, your first instinct, a reasonable one, a deeply human one, is to picture it the way you would picture any bounded region. A sphere, 46 billion light-years in radius, and you at the center. Everything inside the sphere is the observable universe. Everything outside it is not. The boundary is real, fixed, and stable. You are measuring from the middle of something, with a known edge. But this picture smuggles in a concept that doesn't transfer cleanly from everyday geometry to relativistic cosmology. It assumes that radius and distance mean the same thing in an expanding universe, as they do when you're measuring the radius of a room. They don't, and the difference between them is not a minor technical correction. It is the key to why the universe's true size is genuinely unknown. There are, in modern cosmology, at least two distinct ways to measure how far away something is, and they give different answers to the same question. The first is look-back time. When we observe a galaxy whose light took 10 billion years to reach us, we are seeing it as it was, 10 billion years ago. The look-back time is 10 billion years. This is a real, meaningful, measurable quantity. It tells us when the light we're receiving was emitted, and it tells us something about the history of the universe that the light has passed through. In this sense, the furthest objects we can see have a look-back time close to the age of the universe, roughly 13.8 billion years, for the CMB photons. The second is co-moving distance, the distance to an object as it exists now, accounting for the fact that space has been expanding during the entire time the light was in transit. This is the 46 billion light-year figure. It does not represent how far away something was when it emitted its light. It represents where that something is now, after 13.8 billion years of cosmic expansion have continued to push it away from us, while its light was crossing the intervening space. A galaxy whose light took 13 billion years to reach us is not 13 billion light-years away today. It is much further, perhaps 40 billion light-years away or more, because the expansion of space has been carrying it away from us the entire time. This distinction matters enormously for the question we are asking. The observable universe is not a sphere that was 46 billion light-years in radius at some point in cosmic history. It is a sphere that is 46 billion light-years in radius, right now. When you account for all the expansion that has happened since the light we're receiving was originally emitted. The objects whose light is arriving at our telescopes today are not where they were when they emitted that light. They are much, much further away, scattered across a volume, vastly larger than a naive reading of the speed of light would suggest. This is the first layer of the hidden assumption. When we say the observable universe is 93 billion light-years across, We are already doing something more sophisticated than dividing the age of the universe by the speed of light. We are integrating the expansion history of the universe into the calculation, accounting for how space stretched during the photon's journey. The number 93 billion emerges from the mathematics of general relativity, applied to a universe with a specific expansion history, a history that includes matter domination in the early universe, then a transition to dark energy domination that is still ongoing, each phase contributing differently to the overall expansion rate. But here is the second, deeper layer of the hidden assumption, the one that doesn't get mentioned in most popular accounts, because it is more uncomfortable. All of this, the look-back time, the co-moving distance, the 93 billion light-year diameter, applies to the observable universe, the part we can see, the sphere within which information, in the form of electromagnetic radiation, has had time to reach us. And in almost every popular treatment of the cosmos, this sphere is presented as the relevant universe, the universe we care about, the universe we study, the universe to which our theories apply. It contains roughly 2 trillion galaxies, according to a 2016 study led by Christopher Consolis at the University of Nottingham, a figure that revised the previous estimate of several hundred billion galaxies upward by nearly an order of magnitude. 2 trillion galaxies, hundreds of billions of stars in each, and the structure connecting them, filaments, and voids, and clusters, and superclusters, arranged in a cosmic web, whose nodes are some of the densest concentrations of matter in existence. 2 trillion galaxies sounds like enough. It sounds complete. It sounds like a universe. But the observable universe is not the universe. It is the universe as it appears to an observer at our location. At this moment in cosmic time, given the finite speed of light and the finite age of the transparent universe, it is not even the universe as it exists right now. It is a layered time machine, looking at nearby galaxies as they were thousands of years ago, looking at distant galaxies as they were billions of years ago, looking at the CMB as the universe was 380,000 years after the Big Bang. We are not seeing a snapshot of the universe. We are seeing a cone through time, with the past receding in rounings, every direction outward. The assumption hidden in every casual use of the universe, in the context of size comparisons, is that the observable universe is a representative sample of the whole, that the 2 trillion galaxies inside our horizon are arranged in roughly the same way as the galaxies beyond it, that the physics operating inside our sphere applies with the same constants, the same forces, the same rates beyond it, that the universe, in other words, is broadly homogeneous, the same everywhere, on the largest scales, regardless of which 93 billion light-year sphere you happen to be sitting inside. This is called the cosmological principle, and it is not an observation. It is an assumption. Let that settle. The cosmological principle, the foundation on which almost all of modern cosmology is built, the premise that justifies extrapolating from our observable sphere to statements about the cosmos as a whole, is not something we have observed to be true beyond our horizon. It cannot be observed to be true beyond our horizon. because nothing beyond our horizon can reach us. We infer it on the basis of the uniformity we see within our observable sphere, and on the philosophical appeal of the Copernican principle, which states that we are not in a special place in the universe. If the universe is broadly uniform within the region we can see, and we assume that we are not in a specially uniform region while everywhere else is different, then the universe should be broadly uniform beyond our horizon as well. This is a reasonable inference. It may well be correct. The CMB is extraordinarily uniform. The temperature variations across the sky are only 1 part in 100,000, suggesting that the early universe from which our observable sphere emerged was nearly perfectly homogeneous. The large-scale structure of our observable universe, the cosmic web of filaments and voids, appears consistent with what would emerge from those tiny early fluctuations. Under the influence of gravity, over 13.8 billion years, the model works. Internally, it is consistent and extraordinarily well tested. But we cannot see beyond our horizon to verify that the cosmological principle holds there. And there is no logical or physical reason it must. The early universe might have had variations on scales much larger than our observable sphere, variations that would make our local patch look uniform, while the universe as a whole is not. Inflation offers a more unsettling possibility. Regions beyond our horizon might have different physical properties, not merely different arrangements of matter, but different constants, different dimensions, or different vacuum energy states. Not just different arrangements of matter, but different fundamental constants, different numbers of spatial dimensions, different vacuum energy densities. If inflation is right, the cosmological principle may be locally true, and globally, catastrophically, false. And if the cosmological principle doesn't hold beyond our horizon, then the observable universe is not a representative sample. It is a local condition, a neighborhood. And our galaxy-to-universe comparison, our 10 trillion to 1 ratio, is not a comparison of the Milky Way to the cosmos. It is a comparison of the Milky Way to our neighborhood. There is something almost vertiginous in this, if you stay with it long enough. We have built an entire science, cosmology, on the study of a sample whose representativeness we cannot verify. We have derived an age of the universe, an expansion rate, a matter and energy budget, a history from a hot, dense beginning to the current cool, expanding present. And we have done all of this from inside a bubble of observability, extrapolating outward with tools and assumptions that are valid within the bubble and untested outside it. This is not a criticism of cosmology. It is a description of its epistemic situation, a description that the best cosmologists carry with them constantly, that shapes how they phrase their conclusions and how they design their experiments, and that popular accounts almost never convey. Now add one more layer, and this one changes the geometry of the situation in a way that is easy to state, but genuinely difficult to absorb. The 46 billion light-year radius of the observable universe is not constant. It is expanding, not because our horizon is pushing outward into new territory. It isn't, not meaningfully, not anymore, but because of something more subtle and more troubling. The cosmic horizon we are discussing here is actually two different things that are often conflated, and distinguishing them changes the emotional character of the comparison we are making. The particle horizon is the maximum distance from which light could have reached us since the beginning of the observable universe. It defines the outer edge of everything we could, even in principle, have received information from. This is the 46 billion light-year sphere. It grows over time, slowly. Because the universe is old, and new light from previously unreachable regions is gradually arriving, though dark energy is working against this. The event horizon is something different and more unsettling. It is the boundary beyond which events happening now can never send signals that will ever reach us in the future. Not in a billion years, not in a trillion, not ever. Because the universe's expansion is accelerating under the influence of dark energy. There are galaxies that exist today that are visible to us right now, because the light they emitted long ago is still arriving, that are already receding from us faster than light. We can see their past. We will never receive news of their present. Any signal they emit from this moment onward will never reach us, because the expanding space between us and them will carry that signal further away from us, faster than the signal can travel. The event horizon of our universe, is not at 46 billion light-years. It is closer, approximately 16 billion light-years in co-moving distance, based on current measurements of the dark energy density. Galaxies beyond that distance. You are already, at this moment, in the process of sliding permanently out of our communicable universe. Their light from the past still arrives. Their future is already sealed from us. This means that the observable universe is in a peculiar state of decline. It is not shrinking, in the sense that the sphere is collapsing, but it is shrinking, in the sense that the number of galaxies with which we could, even in principle, ever exchange a signal is decreasing. Every moment that passes, more galaxies cross our event horizon, and their futures become permanently inaccessible. We are not just inside a finite observable universe. We are inside a finite observable universe that is slowly contracting around us, in the only sense that matters, the causal sense, the sense of what we can know, and affect, and be affected by. The Milky Way sits inside this sphere, our galaxy, 100,000 light-years across, 400 billion stars. The largest structure any human being can point to and say, "That is mine, that is home," sits inside a bubble of accessibility that is itself shrinking. Not in light-years, but in connections. The ratio of our galaxy to the observable universe is 10 trillion to 1. The ratio of our galaxy to the causally accessible universe will, over the very long run of cosmic time, approach something much more intimate as the accessible universe contracts around us, and eventually leaves us in an island of perhaps only the local group, the Milky Way, Andromeda, and a few dozen smaller companions, as everything else recedes beyond recovery. But we are getting ahead of ourselves, because before any of that future isolation becomes the point, there is still the question of what lies beyond the observable universe. Right now, the question of whether the total universe has a size at all, and what physics has to say about the possibilities. 3 frameworks exist. Each one gives a different answer. Each one is consistent with current observations. And each one, this is the part that starts to feel like a trap. If you have been following the thread carefully, leads to a different and incompatible meaning for the question we started with. How big is the universe? You might expect that question to have one answer. A large number, a unit of measurement, a ratio you can hold still long enough to impress someone. What you are about to discover is that the answer depends not on better telescopes or more sensitive instruments, but on which of 3 possible geometries the universe has a property that our measurements constrain, but cannot yet determine with certainty, and that each possible geometry implies something fundamentally different. About whether size is even the right word to use. The first possibility is that the universe is flat and infinite. The second is that the universe is flat and finite, made so not by geometry alone, but by its topology, the way its spatial structure connects with itself. The third is that the universe is curved and closed, wrapping back on itself like the surface of a sphere, extended into 3 dimensions. Each of these possibilities is, right now, consistent with everything we know. Each implies a completely different answer to the title of this documentary, and the way we distinguish between them, if we can distinguish between them at all, is through measurements of a precision and a subtlety that push cosmology to its epistemological limits. What we measure is the geometry of space, the curvature. We measure it primarily through the CMB, through the angular size of the temperature fluctuations on that background radiation, the characteristic scale at which the early universe's pressure waves imprinted themselves on the plasma, frozen into the CMB, at the moment of last scattering. If the universe is flat, those fluctuations appear at a certain angular scale. If it is positively curved, closed, like a sphere, they appear slightly larger. If it is negatively curved, open, like a saddle, they appear slightly smaller. The current measurements from the Planck satellite, released in 2018, and representing the most precise CMB measurements ever made, indicate that the universe is flat to within roughly 0.4%. Flat. In other words, within the precision of our best measurement. But flat does not mean finite. And it does not mean we can calculate its total size. A flat universe can be infinite, extending in all directions, without boundary, without edge, without return. Or it can be finite, with a topology that makes it wrap back on itself. A 3-dimensional torus, for example, like a video game screen where walking off the right edge brings you in from the left, but extended into 3 spatial dimensions. In such a universe, if you traveled far enough in one direction, you would eventually return to your starting point, just as walking in a straight line along the surface of a sphere eventually brings you back to where you began. These possibilities are not metaphysical. They are geometric. They make predictions. A topologically compact universe would produce specific patterns in the CMB, ghost images of the same structures appearing in multiple directions, statistical correlations at large angular scales, that a simply infinite flat universe would not produce. Cosmologists have searched for these patterns. They haven't found them, which puts a lower limit on the scale of any topological repetition. If the universe does wrap back on itself, it does so on a scale larger than our particle horizon, which means, even in the most compact finite model consistent with observation, the total universe is at least as large as the observable sphere, and possibly much larger. Which brings us, at last, to the question that will carry us into the next descent. If the universe is flat, as our best measurements suggest, and if it is infinite, then the comparison promised by the title of this documentary cannot be completed. You cannot compare the Milky Way to an infinite universe and get a ratio. You get a ratio of 0. The galaxy is not merely small in an infinite universe. It is, in any meaningful mathematical sense, nothing. A finite island in an infinite ocean, whose fractional size is indistinguishable from 0, no matter how many light-years wide it is. If the universe is flat, and finite through topology, the ratio depends on the topology scale, which we cannot measure, because any wrapping is beyond our horizon. And if inflation is correct, if the universe underwent a period of exponential expansion in its first fraction of a second, that stretched it to a size vastly exceeding what any future observation could reveal, then the total universe may be so large, compared to our observable sphere, that the comparison between galaxy and observable universe, as staggering as that 10 trillion to 1 ratio is itself a vanishingly small expression of the true relationship. The clean answer to the title's question is 10 trillion to 1 in volume, galaxy to observable universe. That number is real. It is enormous. It deserves a moment of genuine awe, but it is not an answer to the question you were known to actually asking, because the observable universe is not the universe. It is an edge, a current limit, a confession embedded in a qualifier. And what lies beyond that qualifier is where the real descent begins. The Planck satellite, launched by the European Space Agency in 2009 and decommissioned in 2013, spent 4 years mapping the cosmic microwave background with a sensitivity and angular resolution that exceeded every previous instrument. Its final data releases, particularly the 2018 Cosmological Parameters paper, represent the most precise characterization of the early universe ever achieved. From that data, cosmologists extracted a value for the curvature of space. Technically, the curvature density parameter, designated omega k, of 0.0007, with an uncertainty of plus or minus 0.0019. 0 would mean perfectly flat. The measured value is consistent with 0. It is not 0 with certainty, but it is so close to 0 that the deviation, if real, would be undetectable with any instrument currently planned or conceived. What this means, in physical terms, is that if you drew a triangle anywhere in the observable universe and added its interior angles, they would sum to 180 degrees, to within the precision of our best measurement. In a positively curved space, a closed universe, shaped like the three-dimensional analog of a sphere's surface, those angles would sum to more than 180 degrees. In a negatively curved space, an open universe, shaped like the three-dimensional analog of a saddle, they would sum to less. The observable universe, based on everything Planck measured, is flat, or so close to flat, that the difference cannot currently be resolved. This single measurement carries enormous consequences, and most popular accounts of cosmology state them without pausing to examine the assumption hidden inside. A flat universe, the accounts say, could be infinite, and they move on. But could be infinite is doing a great deal of work in that sentence, and it deserves to be unpacked before anything else is built on top of it. Flatness tells you about geometry. It tells you the local curvature of space, how parallel lines behave, how angles and triangles sum, how the ratio of a circle's circumference to its radius compares to the number pi. What flatness does not tell you is topology. Geometry and topology are related but distinct. Geometry describes the local rules of a space. Topology describes its global structure, how it connects with itself, whether it wraps back, whether it has holes, or handles, or identifications. A flat geometry is compatible with an infinite space that extends in all directions, without return. But it is equally compatible with a finite space that wraps back on itself in a way that preserves the local flatness, a three-dimensional torus being the simplest example, a space in which, if you travel far enough in any direction, you return to your starting point, but in which every local measurement of curvature gives zero. The distinction is not academic. If the universe has a toroidal or other compact flat topology, it has a finite total volume, and therefore a finite total size, even though no local measurement of curvature would reveal this. You would only discover it by detecting the large-scale repetition, the ghost images of structures seen simultaneously in multiple directions, because light has had time to wrap around the universe and reach us from multiple directions. Astronomers have searched for those repeating patterns and found none. If the universe is topologically compact, its repetition scale must therefore extend beyond the region in which such patterns would presently be detectable, which means that if the universe is topologically compact, the repetition scale is larger than our particle horizon, the volume within which any such pattern would be detectable. So the first layer of the problem, flatness, constrains geometry, but not topology. And topology is what ultimately determines whether the universe is finite or infinite. Our measurements push any topological scale beyond our observational reach, but they do not eliminate topological compactness as a possibility. The universe might be finite. We cannot currently determine this. Set that to one side and pursue the infinite possibility first, because it is the one that most cosmologists default to when pressed, and because its consequences for the title question are the most extreme, and philosophically the most destabilizing. If the universe is flat and infinite, what follows? The first consequence is mathematical and immediate. An infinite universe has no total size in the sense of a finite number of light years. Its extent is literally unbounded. You cannot complete the comparison the title promises by expressing a ratio, because a ratio of finite to infinite is not a ratio in any normal sense. It is zero, or undefined, depending on how you frame it. The Milky Way, 100,000 light-years across, is not a small fraction of an infinite universe. It is not a fraction at all. Any finite quantity, divided by infinity, yields zero. Our galaxy, in an infinite universe, has no meaningful size relative to the whole, in exactly the same way that a single sand grain has no meaningful size relative to an infinite beach, not because the grain is particularly small, but because the comparison between a finite quantity and an infinite one is not a comparison in the usual sense. It is a category difference. This is not a rhetorical trick. It is a mathematical reality with physical implications. In an infinite universe, every possible arrangement of matter that is permitted by the laws of physics occurs somewhere. Not might occur, occurs. Because if space is infinite and matter is distributed in it with any finite density, even an extremely low, sparse density, then the number of possible arrangements of matter within any finite volume is itself finite, while the number of such volumes in infinite space is infinite. By pure combinatorics, every configuration must repeat, not once, infinitely many times. What this means, concretely, is that in an infinite universe there are other Milky Way galaxies. Not similar galaxies, not analogues, but exact duplicates, with the same arrangement of 400 billion stars, the same spiral arm structure, the same central black hole of 4 million solar masses, the same small yellow star 26,000 light-years from the center, the same planet in the third orbit of that star, the same arrangement of continents and oceans and mountain ranges, the same history of biological evolution, the same version of you, reading or listening to this sentence for the first time, at this moment. This is not science fiction. It is the direct combinatorial consequence of an infinite flat universe with a finite matter density, a scenario that is consistent with current measurements. The cosmologist Max Tegmark, working from estimates of how far away the nearest such near-duplicate region would be, arrived at a figure of approximately 10 to the power of 10 to the power of 115 meters, a number so large that describing it as astronomical is itself an understatement by a margin that makes the word meaningless. But the distance is irrelevant to the logical point. In an infinite universe, that region exists. It is real. It is physically present. You will never be able to contact it, receive signals from it, or verify its existence. But if the universe is infinite and flat, it is there. Most people, encountering this for the first time, treat it as a curiosity, a fun thought experiment that lives at the boundary between physics and philosophy without really being either. But it is worth sitting with the actual claim being made. The question, how big is the universe compared to the galaxy, has, under this scenario, an answer that is not a number and not a ratio. It has an answer that is, the comparison cannot be completed, because one of the quantities is not finite. And the flatness of space that our most precise measurements suggest is consistent with precisely this scenario. So the flat, infinite possibility dissolves the comparison by making the denominator uncountable. What about the flat, finite possibility, the topological one? Here the consequences are different but equally strange. In a topologically compact flat universe, a 3 torus say, the total volume is finite. The universe wraps back on itself. If you could travel far enough in any direction at any speed, without any restriction, you would eventually return to your starting point. Just as an ant walking in a straight line on the surface of a sphere must eventually return to where it began, but without the sphere's positive curvature. In this scenario, the universe has a definite total volume, a number of cubic light-years, and therefore a definite total size. The comparison the title promises could, in principle, be completed. Galaxy volume divided by total universe volume equals a real number. But here is the problem. The scale at which any such topological repetition occurs, as our searches of the CMB have established, must be larger than the observable universe, which means the total universe, in this scenario, is larger than 93 billion light-years in diameter. How much larger? We don't know. It could be twice as large. It could be 1,000 times as large. It could be just beyond our horizon, or orders of magnitude beyond it. The topology scale is a free parameter that our current observations cannot pin down. They can only put a lower bound on it. The comparison between galaxy and total universe in the finite topological scenario is real but unknown. It is at least 10 trillion to 1 in volume, and it might be enormously larger, but we have no way to measure how much larger from our position inside the observable sphere. We know the numerator, the galaxy, and we have a lower bound on the denominator, but the denominator could be almost anything above that lower bound. Two scenarios. In one, the comparison yields 0. In the other, the comparison yields a real number that we cannot determine. Neither of these is the clean, satisfying, quotable answer that the question seems to demand. And neither of them accounts for the third framework, the one that has the most profound implications, not just for the size of the universe, but for the meaning of the question itself. Cosmic inflation. The theory of inflation was proposed in 1980 by the physicist Alan Guth, then at Stanford, as a solution to 3 problems in standard Big Bang cosmology that were not, on their own, fatal to the theory, but were deeply uncomfortable. The kind of discomfort that accumulates into a crisis if you look at it long enough. The first problem was flatness. In the standard Big Bang model, the flatness of the universe is not predicted. It has to be assumed as an initial condition. But if the universe began with any slight curvature, even a tiny deviation from perfect flatness, that deviation would have been amplified by expansion over cosmic time, producing a universe dramatically curved today. The fact that the universe is flat to within 0.4% is, in the standard Big Bang framework, an extraordinary coincidence. A coincidence that requires the initial curvature to have been fine-tuned to at least 60 decimal places of precision. This is not impossible, but it is the kind of fine-tuning that physicists find deeply unsatisfying. A theory that requires a coincidence to be this precise is usually a theory that is missing something. The second problem was the horizon problem. The CMB is uniform to 1 part in 100,000 across the entire sky. Regions on opposite sides of the visible universe. Regions separated by distances so large that, in the standard Big Bang model, they could never have been in causal contact, never exchanged light or heat or any form of information, have temperatures that match to extraordinary precision. In the standard model, this uniformity has no explanation. Regions that have never been in contact should not be expected to have the same temperature. The fact that they do is another extraordinary coincidence. One that requires vastly separated regions to have started in nearly identical conditions through no mechanism available to standard cosmology. The third problem was the magnetic monopole problem. Grand unified theories of particle physics. The frameworks that attempt to unify the electromagnetic, weak, and strong nuclear forces into a single description predict that in the hot early universe, exotic particles called magnetic monopoles should have been produced in large quantities. They have never been detected. The universe is, observationally, almost entirely free of magnetic monopoles, which is inconsistent with the temperatures reached in the standard Big Bang early universe, unless something happened to dilute them. Guth's insight was that all three problems could be solved simultaneously by a single addition to the standard model. A brief period, very early in the universe's history, during the first tiny fractions of a second after the Big Bang, during which the universe underwent exponential expansion, doubling in size not once but perhaps 60 or 80 or 100 times in a time interval so short it makes any other timescale in physics look geological. During this inflationary expansion, any initial curvature would be stretched away to flatness, just as the surface of a balloon appears flat to an ant on its surface when the balloon is inflated to enormous size. Any monopoles or other exotic particles produced before inflation would be diluted to negligible densities by the enormous increase in volume, and regions that were initially in causal contact, close enough to have reached thermal equilibrium, would be inflated to scales vastly larger than the post-inflation horizon, explaining why the CMB is uniform across the sky. Those distant regions were actually in contact before inflation stretched them apart. The theory was elegant. It solved multiple problems with a single mechanism. And within a few years of Guth's initial paper, it was extended and refined by André Linde, Paul Steinhardt, Andreas Albrecht, and others into what became the inflationary paradigm, the framework that now underlies almost all of modern cosmological thinking about the very early universe. But inflation has a consequence for the size of the universe that is almost never stated plainly in popular accounts, and it is the consequence most directly relevant to the question we are pursuing. If inflation happened, if the universe underwent a period of exponential expansion during its first moments, then the universe is vastly, almost incomprehensibly larger than the observable sphere we can detect. The inflation required to solve the flatness problem, the horizon problem, and the monopole problem simultaneously would have expanded the universe by at least a factor of 10 to the power of 26. A number so large that writing it out in standard notation is essentially meaningless without anchoring it to something comparable. For reference, the ratio of the diameter of the observable universe to the diameter of a proton is approximately 10 to the power of 40. The inflationary expansion factor of 10 to the power of 26 is smaller than that, but it is in the same regime, a regime where intuitive language breaks down entirely. What this means is that the total volume of the universe, if inflation occurred with the parameters needed to explain what we observe, is at least 10 to the power of 78 times larger than the observable volume. The observable universe, those 93 billion light-years, those 2 trillion galaxies, that enormous but navigable sphere of accessible reality, is a subatomic speck within the total post-inflationary universe. The observable sphere is to the total post-inflationary universe what a single proton is to the entire observable universe. It is not a large sample. It is not a representative fraction. It is, in any meaningful sense, nothing. And this is the conservative estimate, because inflation's consequences go further and stranger than simply making the universe very large. Here is the fracture inside inflation's elegance, and it is a fracture that Guth himself recognized, and that has defined much of theoretical cosmology's difficulty for the past 4 decades. In the inflationary models developed through the 1980s and 1990s, the so-called new inflation and chaotic inflation frameworks, developed primarily by André Linde, inflation is driven by a scalar field, a quantum field that fills all of space and carries energy. This field is what causes the exponential expansion. Inflation ends when the field rolls down from a high-energy state to a low-energy state, releasing its energy as the hot plasma of particles that becomes the early universe as we know it. The transition from inflation to hot Big Bang is called reheating, and it marks the beginning of the universe as it is normally described in cosmology. But here is the problem. In the quantum mechanical treatment of the inflationary field, the field does not roll uniformly everywhere at the same time. Quantum fluctuations cause different regions to complete the transition at different times. In some regions, inflation ends early. In others, it continues. And in still others, crucially, inflation is sustained by quantum fluctuations long enough to produce new regions of inflation, which themselves produce quantum fluctuations that sustain further inflation in subregions, which produce further fluctuations, in a process that never terminates globally. Once inflation begins, quantum mechanics almost inevitably makes it self-reproducing, a process called eternal inflation. In eternal inflation, our entire observable universe, the full 93 billion light-year sphere, with its 2 trillion galaxies and its 13.8 billion-year history, formed in a single bubble, a region where inflation ended and reheating occurred. But surrounding our bubble, and separated from it by still inflating space, are other bubbles, regions where inflation also ended, but at different times, with potentially different values for the fundamental constants of physics, different fine structure constants, different masses for elementary particles, different strengths of gravity. These other bubbles are not connected to ours. They are causally separated by the still inflating space between them, space that is expanding faster than light can cross it, such that no signal from any other bubble can ever reach our bubble, and no signal from our bubble can ever reach theirs. These other bubbles are other universes. In the only physically meaningful sense of the word other, they are causally disconnected from us, permanently and completely, with no possible future interaction. Together, our bubble and all the other bubbles constitute what has come to be called the multiverse, a term that carries enormous popular baggage, but which, in this context, means something very specific. An ensemble of causally disconnected regions, each the product of inflation ending at a different time and place, each potentially with different low-energy physics. The multiverse is not a prediction of inflation, in the sense that inflation predicts a specific spectrum of CMB fluctuations. It is a consequence, a feature that emerges from the quantum mechanics of the inflationary field in essentially all realistic models. Guth has estimated that the fraction of inflationary models that do not produce a multiverse is essentially zero. If inflation happened, and the evidence from the CMB strongly suggests that something like inflation happened, then the multiverse almost certainly exists. Now hold this alongside the question we have been pursuing. How big is the universe compared to the galaxy? If the multiverse is real, the word universe in that question has no stable referent. We might mean our observable sphere. We might mean our causal patch, the region with which we can ever, even in principle, interact. We might mean our bubble. the post-inflationary region that shares our low-energy physics, vastly larger than our observable sphere, but still finite in the sense of having been produced by a single reheating event. We might mean the entire multiverse, the ensemble of all bubbles, all post-inflationary regions, the total extent of space produced by eternal inflation. The last of these has no boundary, no total size, no well-defined extent, because eternal inflation is ongoing. New bubbles are forming now, and will form forever, in the still inflating medium between existing bubbles. The multiverse is not a static structure with a fixed size. It is a process, an ongoing expansion that has no termination in our future and possibly no beginning before the start of inflation itself. If the question, "How big is the universe?" means the multiverse, the answer is not a number. It is not even an infinity of a particular size. It is a process in a state of permanent growth, to which no measurement from inside any single bubble can ever contribute, and to which no concept of a fixed total size applies. The clean comparison, galaxy to universe, 10 trillion to 1, was already complicated by the distinction between observable and total. Inflation complicates it further by making total potentially mean all bubbles ever produced by eternal inflation, a set that is not bounded and for which no size can be defined. But before this descent can continue any further, it needs to reckon with an objection, one that many physicists take seriously and that has sharpened over the past 2 decades into one of the central debates in theoretical cosmology. The objection is this: the multiverse is not a scientific theory. It is a metaphysical appendage to a scientific theory. The argument runs as follows. Science derives its power from the ability to make predictions that can be tested, observations that would, if the theory is wrong, show the theory to be wrong. A theory that is consistent with any possible observation is not a scientific theory. It is a philosophical position dressed in mathematical language. The multiverse, as a consequence of eternal inflation, makes no predictions about our observable universe that eternal inflation alone does not also make. There is no observation you could make inside our bubble that would confirm or deny the existence of other bubbles, because the other bubbles are causally disconnected from ours. The multiverse is therefore, in the strict Popperian sense, unfalsifiable, and unfalsifiable claims fall outside the domain of empirical science. This objection is taken seriously by physicists of the highest caliber. Paul Steinhardt, Roger Penrose, and others have made versions of it, and it has a sharp edge that is worth dwelling on. If you accept the multiverse as a consequence of inflation, you have accepted that the universe, in the sense of everything that physically exists, is vastly larger than anything observable, and that this additional extent is not just currently unobserved, but is in principle unobservable. You have, in other words, expanded the definition of what exists beyond the reach of any possible evidence. This is a move that some physicists regard as a necessary consequence of taking the mathematics seriously, and others regard as a category error, a confusion between what the mathematics implies and what physically exists. The defenders of the multiverse respond with several arguments. First, the multiverse is not introduced ad hoc to explain any particular observation. It is a consequence of the dynamics of inflation. It falls out of the mathematics without being put in by hand. Second, inflation itself makes precise, testable predictions about the spectrum of CMB fluctuations, the flatness of space, the scale invariance of primordial density perturbations, and those predictions have been confirmed to extraordinary precision. The multiverse comes packaged with confirmed predictions. You cannot surgically remove the multiverse from inflationary theory without altering the theory in ways that have observable consequences. Third, we regularly accept as real things that we cannot directly observe: the interior of black holes, the quantum state before measurement, events in our own past light cone that happened before we existed. Observability is not the only criterion for physical reality. None of these arguments fully resolves the objection, and the debate remains genuinely open. What is certain is that the question, "How big is the universe?" cannot be answered without first deciding which framework you are operating in, and that the framework most consistent with the physics of the early universe, inflation, implies a universe vastly larger than what we can observe, and possibly implies a collection of universes for which no single size can be defined. The partial answer arrived at so far is this: the universe is at least as large as our observable sphere, probably enormously larger, and if inflation is correct, the total extent of everything that exists may be either incomparably large or genuinely boundless, in a way that makes size comparison undefined. This is the point at which a documentary about cosmic scale would normally reach for awe: the vast numbers, the incomprehensible distances, the mise-en-scène of human smallness. But smallness is not quite what we have arrived at. We have arrived at something more precise and more unsettling than smallness. We have arrived at the possibility that the denominator in our comparison, the size of the universe, is not a fixed quantity waiting to be measured, but a framework-dependent variable that changes its value and possibly its meaning depending on which physics you accept. The Milky Way has a definite size: 100,000 light-years, give or take. It can be measured from outside, in principle. Its mass can be estimated, its rotation curve mapped, its stellar population surveyed. It is a real, bounded, measurable physical object, whose properties do not depend on which cosmological framework is correct. The galaxy is the stable term in the comparison. The universe is not. And this asymmetry, the stability of the galaxy against the instability of the universe as a concept, is the deeper paradox underneath the question. Not that the galaxy is small. That the thing it is being compared to may not have a stable definition that is independent of the position and assumptions of the comparer. There is a moment in the history of science that this situation resembles, not in its specifics, but in its structure. It is the moment, in the early 20th century, when physicists discovered that the mass of an electron depended on how fast it was moving, that the length of an object depended on the observer's reference frame, and that the simultaneity of events separated in space depended on the relative motion of the observers comparing them. Before relativity, mass, length, and simultaneity were observer-independent properties, real, fixed, measurable quantities that everyone would agree on, regardless of their position or motion. After relativity, they became observer-dependent. They were still real, still measurable, but each observer's measurement was valid only within their reference frame, and no measurement could be called the absolute truth about the object being measured. The situation with the universe's size is analogous, though not identical. Within our observable sphere, size is observer-independent. Everyone inside this sphere, making measurements with the same physics, will agree on the size of the galaxy, the distance to the Andromeda galaxy, the diameter of the observable sphere. But once you ask about the size of what lies beyond the observable horizon, you have left the domain of observer-independent measurement. The answer depends on the cosmological framework: flat and infinite, flat and topologically compact, inflationary with or without eternal inflation, with or without a multiverse. And those frameworks are not, currently, distinguishable from our position inside the observable sphere. The size of the universe is, in this sense, an observer-dependent property, not because different observers would measure different values using the same physics, but because the universe, to which any measurer has access, is always and only the observable sphere surrounding that measurer. What lies beyond is not accessible to measurement by any observer, from any position, and the properties ascribed to it are inferences based on theoretical frameworks rather than measurements. A third framework now enters the argument. It is less dramatic than an infinite universe or a multiverse, but potentially more precise, because it begins with the flatness we actually observe. Less dramatic than the infinite flat universe or the multiverse, but perhaps more physically precise, because it takes the observed flatness seriously and asks what constraints that flatness, combined with everything else we know, actually places on the total extent of space. The framework is called the finite inflation model, or, more precisely, the minimally extended inflationary universe. It accepts inflation as real and necessary, but asks, what is the minimum inflationary expansion required to explain what we observe, without invoking eternal inflation and without assuming anything about regions causally disconnected from ours? The answer is a universe that is finite, post-inflationary, and enormously but not infinitely large. A universe whose total extent can be estimated in terms of the minimum inflationary expansion factor consistent with solving the flatness and horizon problems. In the most conservative such estimates, the total universe is at least 10 to the power of 23 times the volume of the observable sphere. That is 100 sextillion times larger. In this framework, the ratio of the Milky Way to the total universe is approximately 10 to the power of 36, far beyond the 10 trillion to 1 ratio of galaxy to observable universe, and far beyond any number that can be meaningfully communicated by analogy. If the observable universe is the Pacific Ocean and the galaxy is a bathtub, then the total minimum inflation universe is to the observable universe as the Pacific Ocean is to a single water molecule. But this is still a finite number. Still, in principle, a comparison that can be completed, even if its magnitude is beyond human intuition. It is an answer. A strange one, an enormous one, a nearly meaningless one, but an answer. The problem is that the minimum inflation scenario is not the most likely inflation scenario. It requires the inflation field to have ended in a way that is fine-tuned to produce exactly the minimum expansion. A fine-tuning that is itself a kind of cosmological coincidence, the same class of coincidence that inflation was supposed to eliminate. Most models of the inflationary field predict much more expansion than the minimum, and most predict eternal inflation as a natural consequence of the quantum dynamics. The minimum inflation scenario is theoretically possible but dynamically unlikely, in the same way that a single perfect crystal of ice forming spontaneously in a glass of water is thermodynamically possible but vanishingly unlikely. So the three frameworks, flat infinite, flat topologically compact, and inflationary, each give a different answer to the question of the universe's total size. The first says, the comparison yields 0. The second says the comparison yields an unknown real number greater than 10 trillion to 1 in volume. The third says the comparison yields either a very large finite number or something that cannot be expressed as a finite number at all, depending on whether eternal inflation is incorporated. And there is, critically, no observation currently possible that can distinguish between these three possibilities from our position inside the observable sphere. The measurements that would distinguish a flat geometry from a slightly curved one require sensitivity beyond current instruments. The measurements that would detect topological repetition require patterns in the CMB that searches have not found. The measurements that would confirm or rule out eternal inflation would require access to other bubbles or to the inflating medium between them, access that is physically impossible in principle, not just in practice. This is not a temporary problem. It is a structural feature of our epistemic situation. We are inside a finite observable sphere, measuring a universe whose total extent depends on theoretical frameworks that cannot be tested from inside the sphere. The inability to answer, "How big is the universe?" is not a gap in our knowledge that will be closed by better telescopes. It is a consequence of the physics of horizons and expansion that is, in the most precise sense of the word, permanent. Which brings the descent to the question that changes everything that came before it. If three different frameworks give three incompatible answers to the size of the universe, and none of the answers can be confirmed or refuted from our position, what is the question actually asking? What kind of question is, "How big is the universe?" if it cannot, even in principle, have a verified answer? There are several ways to respond to this. The pragmatic response, the one most working cosmologists would give, is that the question is perfectly meaningful within the observable sphere, and that the extension to total size is an interesting theoretical question, even if it is currently empirically inaccessible. The answer within the observable sphere is 10 trillion to 1 in volume, galaxy to observable universe, and that is real and important and worth knowing. The extension beyond the observable sphere is a different question, a theoretical question, and while it is interesting, its current inaccessibility does not make it unanswerable in principle. It just means we need different tools or approaches, some of which may be possible in the future, and some of which may not. The philosophical response, the one that the structure of the problem seems to demand, is more uncomfortable. It suggests that size as a concept may not be coherently applicable to the total universe, in the same way it is applicable to the galaxy. The galaxy has a size because it has edges, places where the density of stars drops off dramatically, where the gravitational influence of the central mass becomes subdominant to the gravitational influence of the surrounding larger-scale structure. The galaxy can, in principle, be measured from outside. Another observer in a distant galaxy could, in principle, measure the Milky Way's angular extent and infer its diameter. The galaxy has a size the way a coin has a size. It is an object with a boundary, embedded in a larger context, whose properties do not depend on who is measuring it. The universe has no outside. There is no vantage point from which it can be measured as an object embedded in something larger. Every measurement of the universe's size is made from inside it, using tools and information that exist inside it. And the result of every such measurement is a measurement of the measurer's horizon, not of the universe's extent. The 93 billion light-year diameter of the observable universe is not the size of the universe. It is the size of our observable sphere. The distinction matters because the galaxy's size is a property of the galaxy. The observable sphere's diameter is a property of the observer's position and the age of the transparent universe. A relational property, not a property of the universe itself. This argument has a precise parallel in thermodynamics and information theory. In thermodynamics, entropy is sometimes described as a property of a system, but more accurately, it is a property of a system relative to the observer's knowledge of the system's microstate. A system whose microstate is fully known has zero entropy from the perspective of the fully informed observer. The same system has high entropy from the perspective of an observer who knows only its macrostate. Entropy is not a property of the system alone. It is a property of the system relative to the observer's information. The universe's size is analogous. It is not a property of the universe alone, but a property of the universe relative to the observer's position, the age of the transparent era, and the framework of physics the observer uses to extrapolate beyond the horizon. Now consider what this means for the central paradox we opened with. The galaxy feels vast, and it is vast, by any everyday measure. The universe feels incomparably larger, 10 trillion times larger in volume, by the standard comparison. But the universe's size in that comparison is a horizon, a relational property, a measurement of our position and our physics, not of the universe as an observer-independent object. When we say the galaxy is 10 trillion times smaller than the universe, we are saying something true about the galaxy and the observable horizon. We are not saying something definitive about the galaxy's relationship to the total universe, because the total universe's size is framework-dependent and currently indeterminate. This is the moment to introduce what might be called the scale paradox, the specific contradiction that gives this mode its name, the nested structure of failed explanations that each solve one problem while revealing a stranger one beneath. At the first level, the paradox is simple. The galaxy is enormous, but compared to the observable universe, it is almost nothing. This seems like the whole story. It isn't. At the second level, the paradox deepens. The observable universe is not the universe. It is our horizon. The universe beyond our horizon may be vastly larger, perhaps infinitely larger, in which case even the observable universe itself, all 93 billion light-years of it, is almost nothing relative to the total. The galaxy is nothing relative to the observable universe. The observable universe is nothing relative to the total. The galaxy is therefore doubly nothing, nothing relative to nothing. At the third level, the paradox dissolves into something stranger. If the universe is infinite, or if the multiverse is real, then nothing relative to the total is not a relationship at all. It is the mathematical fact that any finite quantity has measure zero in an infinite set. The galaxy is not small relative to an infinite universe. The galaxy has no size relationship to an infinite universe, because size relationships require comparable quantities, and finite and infinite are not comparable. The comparison the title promised cannot be completed. The denominator is not a number. At the fourth level, the deepest layer reached so far, the paradox becomes reflexive. The very concept of size that makes the galaxy measurable is a concept that applies within bounded, measurable systems, and the universe is not bounded or measurable from any external perspective. The galaxy has a size because it has edges. The universe has no edges, or if it does, Those edges are beyond any possible observation. Size, as a physically meaningful concept, may be inherently local, applicable within the observable sphere, where all measurement takes place, but inapplicable to the universe as a whole, where no external measurement is possible. Each level of this descent solved the previous problem and revealed a deeper limitation. The first level gave a number, 10 trillion to 1. The second level revealed that the number's denominator was a horizon, not the universe. The third level showed that the denominator might not be a number at all. The fourth level suggested that the concept being applied, size, might not be applicable to the universe in the way it is applicable to things within it. This is the structure of a genuine paradox. Not a logical contradiction, but a situation in which successive attempts to answer a question reveal that the question was asking for something that the structure of reality does not supply. The question, how big is our galaxy compared to the universe, seems to ask for a ratio, but a ratio requires two comparable quantities. And the universe, as a whole, may not be a quantity in the sense required. None of this means the question is meaningless. The observable universe has a size, a real, measurable, physically definite size, the result of applying general relativity to a universe with known matter and energy content and a known expansion history. The galaxy has a size, equally real, measurable, definite. The ratio is real. The 10 trillion to 1 figure is true and important, and genuinely illuminating about the scale of structure in our observable cosmos. What it is not is an answer to the question of how big the galaxy is compared to the universe, because the universe, as a whole, rather than as an observable sphere, does not have a size in the sense the question requires. This is not a failure of science. It is a discovery. The discovery is that the concept of size, applied globally to the universe rather than locally within it, becomes undefined in a way that is not an accident of our ignorance, but a consequence of the most fundamental features of space, time, expansion, and observation. One more thread changes the meaning of everything established so far, by making cosmic scale personal in a way that numbers alone cannot. The cosmic microwave background, that thermal afterglow of the moment of transparency, 380,000 years after the Big Bang, is not perfectly uniform. It is nearly perfectly uniform, 1 part in 100,000. But the tiny fluctuations that remain are not noise. They are signal. They are the imprint of quantum fluctuations in the inflationary field, stretched to cosmological scales by inflation, seeded into the density of the early plasma, and frozen into the CMB at the moment of last scattering. Those fluctuations are the seeds of all structure in the observable universe. Every galaxy cluster, every filament in the cosmic web, including the Milky Way, grew from a quantum fluctuation in the inflationary field that was stretched to galactic scale by inflation and then amplified by gravity over 13.8 billion years. The galaxy is not just sitting inside the universe. The galaxy grew from a specific fluctuation in the inflaton field, a particular ripple in the quantum foam of the inflationary era that happened to produce, in our region of space, a density excess of the right magnitude and scale to eventually collapse into a 100,000 light-year spiral disk with 400 billion stars. Our existence, not just humanity's existence, but the galaxy's existence, is contingent on that fluctuation. A slightly different fluctuation in the same region, and the galaxy might have been smaller, or larger, or might never have formed at all. The fluctuation that produced us was one of an effectively infinite number of fluctuations that inflation produced across the observable sphere and far beyond it. In the infinite universe, or the multiverse, every possible fluctuation occurs. Every possible galaxy forms somewhere. The Milky Way is one realization of the space of possible post-inflationary density fluctuations, and it is the one we happen to form in and on and from. In this sense, the galaxy is not just inside the universe. The galaxy is a selection, a specific outcome drawn from the distribution of possible outcomes that the physics of inflation produces. And here, for the first time in this descent, the comparison between galaxy and universe ceases to be purely a comparison of scales. It becomes something else. The galaxy is a consequence of the universe's quantum structure, a specific, irreducibly local product of a process that operated across scales so far beyond the galaxy as to be effectively global. The galaxy is smaller than the universe, in the way that a sentence is smaller than the language it is written in. Not just contained within it, but produced by it, constrained by it, a specific expression of its generative capacity. The universe produced the galaxy. The galaxy contains the question about the universe. And the question, pursued far enough, reveals that the universe cannot be the kind of thing the question assumes, a fixed, bounded object with a definite size, waiting to be measured and reported. It is something else, something that the language of size and comparison describes locally, within the observable sphere, and fails to describe at the scale of the whole. What is the universe at the scale of the whole? What property does it have, if size is the wrong concept? What framework is adequate to describe something that cannot be observed from outside, cannot be measured in total, and whose extent depends on which physical theory is correct? Current physics cannot answer that question. But following these three frameworks has produced a more precise version of it, one that asks whether size itself remains meaningful at the scale of the total universe. The galaxy is 100,000 light-years wide, that is certain. Everything else, the universe's true extent, its topology, its relationship to other possible universes, the framework within which it can meaningfully be said to have a size, is unsettled. Not in the way that unsettled scientific questions are eventually settled by better instruments. In the way that some questions, pursued far enough, reveal that the answer requires a concept not yet invented. That is where we are, not at the bottom of the paradox. At the point where the paradox becomes exact enough to be productive, where the question is no longer, how big is the universe, but what would it mean for the universe to have a size, and does the universe supply that meaning, or is it something we bring to it from our position inside? That question is the next descent, and it begins with you. There is a specific kind of loneliness that has nothing to do with the absence of other people. You can be surrounded by everyone you have ever known, in a room full of warmth and noise and connection, and still feel it, the particular vertigo that comes from recognizing, suddenly and without warning, that the place you are standing is not the stable ground you assumed it was, that the floor is floating, that the walls are not walls but boundaries of perception, beyond which something immense and indifferent extends without limit. It is not sadness. It is not fear. Exactly. It is the sensation of scale arriving in the body before the mind has finished processing it, a physical apprehension of one's own finitude against something that does not share that finitude. What the science established in the previous descent produces, if you follow it honestly to its end, is a version of that sensation, not as metaphor, but as the literal consequence of measurements made with the most precise instruments humanity has ever built. Let us make it specific. Let us make it yours. You are on Earth. This is not a poetic simplification. It is the most precise statement of your location in the structure we have been describing. You are on a planet orbiting a star 26,000 light-years from the center of the Milky Way, in a minor spiral spur, in a galaxy 100,000 light-years across, in a local group of perhaps 54 gravitationally bound galaxies, in a larger structure called the Virgo supercluster, itself part of a structure called Laniakea, a supercluster 500 million light-years across, containing perhaps 100,000 galaxies, and a total mass of 10 to the power of 17 solar masses. And Laniakea is itself one node in a cosmic web of filaments and voids that extends, in our observable sphere, out to 46 billion light-years in every direction. That is your address. Every component of it is real and measured. None of it is metaphor. Now consider what you can reach from that address. Not in the near future, not with hypothetical technologies. In any future, across any timescale that physics permits, using any means that the laws of nature do not prohibit. Across all of cosmic time, from now until the last moment at which any structure remains capable of doing anything, what is the total region of the universe with which anyone or anything originating here could ever interact? The answer is defined by the event horizon, not the particle horizon, which describes what we can currently see. The event horizon, which describes the boundary beyond which no future signal will ever reach us, and beyond which nothing we send will ever arrive. The event horizon of our observable universe, as determined by current measurements of dark energy density and expansion rate, sits at approximately 16 billion light-years in co-moving distance. Not 46 billion, not 93 billion, 16 billion. Every galaxy currently visible beyond 16 billion light-years is already, at this moment, in the process of becoming permanently unreachable. Not gradually, not in some theoretical limit. Now. The expansion of space is carrying those galaxies away from us faster than any signal could follow. Their light from the past still arrives, will continue to arrive for billions of years, red-shifting as it comes, fading as the wavelength stretches. But any signal we send toward them today will never get there. Any signal they emit today will never reach us. The causal connection between our position and those galaxies is already severed, in the only sense that matters physically, the sense of what can cause what. There are approximately 2 trillion galaxies in the observable universe. The number within our event horizon, the number with which any future interaction, of any kind, is physically possible, is a small fraction of that. Estimates vary depending on exactly how the event horizon is defined and how galaxy counts are distributed. But the rough picture is that the vast majority of the observable universe's galaxies are already beyond causal reach. We can see them. We cannot touch them. We cannot signal them. We cannot be affected by anything happening in them now or ever again. This is not a temporary condition pending technological improvement. It is the permanent physical state of our position in an accelerating universe. Dark energy, the component of the universe's energy budget responsible for the accelerating expansion, constituting roughly 68% of the total energy density, is not going away. Every measurement suggests it is constant, or very nearly constant, a property of space itself rather than a decaying field. If it remains constant, the expansion will continue to accelerate indefinitely, and the event horizon will remain roughly where it is, slowly tightening around us as the universe ages, as the galaxies within reach age and fade, and eventually exhaust their stellar populations. In the very long run, on timescales of trillions of years rather than billions, the region of the universe accessible to any observer at our location will shrink not in light years but in content. The Milky Way will merge with Andromeda in approximately 4.5 billion years, forming a new elliptical galaxy, sometimes called Milkomeda. The local group, those 54 gravitationally bound companions, will eventually merge into a single enormous galaxy, a final gravitational island, whose stars gradually exhaust their nuclear fuel, whose gas reservoirs are slowly consumed or ejected, whose stellar remnants cool and dim over timescales that make the current age of the universe look negligible. Everything outside the local group, every other galaxy, every other cluster, every other supercluster, will have receded beyond our event horizon, long before this final island goes dark. The universe visible from our position will consist, in its old age, of our local merged galaxy and an otherwise empty, expanding void. This is what the physics actually implies. Stated plainly, our causal island is not a sphere 93 billion light-years across. It is a sphere approximately 16 billion light-years across, shrinking in content with every passing moment, destined to contract around us until all that remains is the single gravitationally bound structure we already inhabit. Feel that, not as a number, as a condition. Every star you can see with your naked eye on a clear night is inside our galaxy. Every one of those stars is within our causal reach. They are part of the island. Every galaxy visible to the eye, the Andromeda galaxy, a smear of light in the constellation Perseus on a dark night, 2.5 million light-years away, is within our local group, within the island. Even the most distant objects visible to powerful telescopes, billions of light-years away, are within the event horizon. For now. But the universe beyond, the 84% or more of the observable universe that lies beyond our event horizon, the uncountable galaxies whose light is still arriving from their pasts while their futures slide away from us. That universe is not ours. It never was, in the causal sense. It shares our Big Bang, our physics, our fundamental constants, but it does not share our causal future. It is, in the only sense that physics validates, separate, not metaphorically separate, physically, causally, permanently separate. Here is where the existential weight becomes specific to this title. The comparison between galaxy and universe, the 10 trillion to 1 ratio, was always implicitly a comparison of scale within a shared causal structure. The observable universe contains our galaxy the way a country contains a city. They are part of the same physical network, connected by geography and causality, such that events in one can influence events in the other. But the actual universe, the total universe, including everything beyond the event horizon, does not contain our galaxy in that sense. It contains our galaxy in the sense that a dictionary contains a single word, present within it, but without any causal pathway from the rest of the dictionary to that word, or from the word to the rest. The galaxy is not just small relative to the universe. The galaxy is causally isolated from most of the universe. not because of distance alone, but because the expansion of space has structurally severed the connections that would make most of the universe causally relevant to us. The comparison between galaxy and universe is not a comparison between a small part and a large whole. It is a comparison between a causally coherent island and a vast surrounding ocean, with which the island has no causal commerce, and never will. This is where ordinary awe gives way to a more specific kind of vertigo. The isolation is not temporary or technological. It is structural. Not ordinary awe at large numbers, but the specific vertigo of recognizing that the isolation is not contingent, not a matter of distance that might one day be overcome with better technology or faster ships. The isolation is structural. It is written into the geometry of space-time by the presence of dark energy and the finite speed of light. No future civilization, however advanced, however patient, however ingenious in its use of physics, can reach a galaxy currently beyond our event horizon. The causal connection does not exist. It cannot be created. The universe does not permit it. There is a thought experiment that clarifies the specific nature of this isolation, and it is worth staying with it for a moment. Imagine that on a planet orbiting a star in a galaxy currently at 20 billion light-years from us, just beyond our event horizon, a civilization identical to ours has just built its first radio telescope. At this moment, they are scanning the sky for signs of other civilizations. They are asking the same questions we ask. They are looking at the same cosmic web, the same CMB, the same large-scale structure. Their physics is identical to ours. Their curiosity is identical to ours. They are, in every physical sense, our counterparts, separated not by nature or by history, but purely by the accident of which density fluctuation in the early universe produced their galaxy versus ours. They cannot find us, not because their technology is insufficient. No technology, at any level of sophistication, could find us, because the causal pathway between their position and ours no longer exists. Any signal they send toward the region of sky where the Milky Way appears in their sky will never arrive here. Any signal we send in their direction will never arrive there. We are not hidden from them by distance. We are hidden from them by the geometry of an accelerating universe, as definitively and permanently as events before the Big Bang are hidden from the present. We coexist in the same physical universe. We are products of the same Big Bang, governed by the same laws, and we are as causally isolated from one another as if we existed in separate universes entirely. And they exist. Or something exists, beyond our horizon, because the cosmological principle, imperfect inference that it is, suggests that the universe beyond our sphere is not radically different from what's within it. There are galaxies out there. There are stars. There is, almost certainly, the same kind of structural complexity that produced us here, and none of it can ever, under any physical law we know, participate in the same causal story as we do. This is not the horror of insignificance. The emotional register of this realization is more precise than that. Insignificance implies that you exist within a context that dwarfs you, that you are present in something enormous, subject to its influence, visible within it even if barely. What the event horizon implies is something different, not that we are small within the universe, but that most of the universe is not, in the causal sense, our universe at all. The Milky Way is not a small island in a vast connected ocean. It is a small island in a vast, disconnected archipelago, where the other islands are physically unreachable, not because they are far away, but because the water between them is expanding faster than any vessel could travel. The distinction between those two images, small island in a connected ocean versus small island in a disconnected archipelago, is the distinction between the ordinary awe of cosmic scale and the specific existential condition that follows from the physics of dark energy and causal horizons. The first image preserves connection, the second destroys it, and the second is the one that corresponds to the actual physical situation. Now push this one step further, because the isolation is not just spatial, it is temporal in a way that deepens the condition. When you look at the night sky, you are not seeing the universe as it is. You are seeing it as it was at different moments in its history, each moment corresponding to the time it took the light from each object to reach you. The moon as it was 1.3 seconds ago. The sun as it was 8 minutes ago. The nearest star, Proxima Centauri, as it was 4.24 years ago. The Andromeda Galaxy as it was 2.5 million years ago. The most distant galaxies visible in deep-field images, those faint smears of ancient light at the edge of our telescopic reach, as they were 10 or 12 or 13 billion years ago, when the universe was young and those structures were forming for the first time. The sky is not a snapshot of the universe now. It is a layered archive, a record of different moments in cosmic history, compressed onto the two-dimensional surface of your visual field, with distance serving as a proxy for age. Looking outward is looking backward. The furthest thing you can see is the furthest thing in the past. And the CMB, the furthest thing of all, the background glow in the microwave frequencies that represents the wall of the observable universe, is the universe as it was 380,000 years after the Big Bang, not billions of years ago. 380,000 years after the beginning of the transparent universe. 14 billion years in the past. What is happening in the region corresponding to the CMB right now? What has been happening there for 13.8 billion years while its ancient light was traveling toward us? We cannot know, not approximately, not with inference. We genuinely, completely, cannot know, because no signal from that region since the moment of last scattering has had time to reach us. The CMB is not a window onto a distant region of the universe. It is a sealed record of a single moment, from a region whose subsequent history is permanently beyond our reach. The visible universe, in other words, is not just causally isolated in space. It is causally isolated in time. Every observation we make reaches backward. Every piece of information we have about distant regions is old information, sometimes ancient, sometimes unimaginably ancient. We are embedded in the present, but our knowledge of the universe's extent is built entirely from its past. We see the universe not as a spatial structure existing simultaneously with us, but as a temporal onion, layer after layer of increasingly ancient states, with the current state of the universe beyond our horizon completely unavailable to us. There is something specifically strange about this, if you hold it at the right angle. The universe is old enough, 13.8 billion years, and large enough, 93 billion light-years in radius, that the light arriving at our telescopes from its furthest reaches was emitted before the Milky Way existed. The galaxy you live in was not there when that light began its journey. The light from the CMB was already more than 9 billion years into its journey when the solar system formed. It was more than 4 billion years old when Earth formed. It had been traveling for nearly 9 billion years when the first photosynthetic bacteria began producing oxygen in Earth's ancient oceans. The light that reveals the edge of the observable universe began before the galaxy began. The universe's history predates its structures. This is not merely interesting. It is a statement about what kind of thing the universe is relative to the things within it. The galaxy is a local structure, a condensation of matter that formed in a specific place and time, within a universe that predates it by 9 billion years and extends beyond it by 46 billion light-years in every direction. The galaxy did not emerge from the universe the way a child emerges from a parent. It emerged from the universe the way a wave emerges from the ocean, a local pattern of organization in a medium vastly older, larger, and less structured than the pattern itself. The wave is real. It has height and speed and form. It is genuinely there, but it is not the ocean. It is a temporary expression of the ocean's energy, lasting for the moment that the conditions sustain it, and eventually subsiding back into the medium from which it arose. The Milky Way is a wave, enormous by any standard we normally use, real, structured, containing within it every star that has ever been observed, every planet ever visited or imagined, the entire history of life on Earth, and whatever other histories exist on whatever other worlds orbit whatever other stars. But a wave, a temporary local pattern in a medium, the universe, that is older, larger, and indifferent to the pattern's local significance. And most of the ocean is beyond our horizon. Most of the medium is permanently unreachable. The wave we call our galaxy is not just small relative to the ocean. It is causally disconnected from most of it, a local pattern in a medium most of which it cannot touch, cannot signal, cannot influence, and cannot be influenced by. The isolation is complete. It is structural. It is written into the laws of physics. Here is the full weight of that, not the poetic version, the physical version. Everything that has ever mattered, every civilization, every scientific discovery, every moment of beauty or grief or connection in all of human history, every equivalent moment in whatever other histories exist in the universe accessible to us, happened inside a causal island that represents a small fraction of the observable universe, which is itself a small fraction of the total universe, which may itself be a small fraction of everything that exists. The entire domain of what can ever cause anything, or be caused by anything, as seen from our position, is a bubble approximately 16 billion light-years across, in a universe that stretches, by how much, we genuinely do not know, further than that number, in ways that are not connected to our bubble by any physical law. And within that bubble, within that 16 billion light-year sphere of causal relevance, within everything that has ever mattered, or ever will matter from our perspective, the Milky Way occupies a region 100,000 light-years wide, not small by any everyday measure, small in the only comparison available. The number is not 10 trillion to 1. That was the comparison of galaxy to observable universe. The comparison of galaxy to causally accessible universe depends on how you define the accessible region, and it is not a ratio that produces satisfaction. The galaxy is almost everything we have ever touched, and it is a negligible fraction of what we can see, and what we can see is a fraction of what exists, and what exists is either infinite or so large that the word large carries no meaning at the scale required. And yet, Here is where the emotional register must be very precise, because it would be easy to reach for despair, and it would be inaccurate to do so. The isolation is real. The scale is real. The contingency of the galaxy's formation, one quantum fluctuation among an effectively infinite number, is real. But despair would require the assumption that scale determines significance, that the size of a thing determines its importance, that a wave is less real than the ocean because the ocean is larger. Nothing in physics supports that assumption. Physics describes scales and causal relationships. It does not describe importance. The Milky Way is causally isolated from most of the universe, and the Milky Way is the only place from which questions about the universe have ever been asked. Those two facts are equally true. The isolation and the inquiry coexist. The wave is small, and the wave contains the capacity to ask about the ocean. There is something in that coexistence that is not comfortable, but is not despairing either. It is a third thing, a condition that has no good name in ordinary language, but that the science of this question produces as a logical consequence. The galaxy is isolated. The galaxy is the site of all knowledge. The universe is mostly unreachable from the galaxy. The galaxy is the only place from which the universe has been measured. These facts form a structure, and the structure is not hierarchy. It is not that the universe is more important because it is larger, or that the galaxy is more important because it contains the questioners. It is something more like mutual dependency. The universe produced the galaxy, and the galaxy is producing the only account of the universe that will ever be made from this position, in this causal island, in this bubble of space-time that dark energy has sealed from the rest. That account, the one being built by every telescope and particle detector and theoretical framework that human inquiry has produced, is not a complete account of the universe. It is an account of our island, an account of what can be known from here. And the question of whether that account is representative of the universe as a whole, whether our island is typical, whether the physics we have derived from it holds everywhere, whether the story we are telling about the cosmos is the universe's story or just our neighborhood story, is a question that the causal structure of space-time prevents us from answering. We are not just inside the universe, measuring it. We are inside a specific, sealed region of it, measuring what we can reach, and inferring the rest from frameworks that cannot be verified by any observation from inside the seal. The galaxy is our platform. The observable sphere is our library. The event horizon is our wall. Beyond the wall, the universe continues. By how much and in what condition, we do not know, and the wall is not temporary. It is not a challenge waiting for a more determined civilization to overcome. It is the geometry of space in an accelerating universe, and it is as permanent as the speed of light. This is the existential condition that the title's question, followed honestly to its physical consequences, produces. Not smallness, not insignificance. Something more precise and more strange. Complete causal adequacy within the island. Complete causal isolation from outside it. And the permanent inability to know how much of the total universe the island represents. The galaxy is enormous, and it is everything we have. The universe is incomparably larger, and most of it is forever beyond reach. The comparison between them is real, and it is also the wrong question. Or rather, it is the right question asked at the wrong scale, asking for a ratio when the structure of the problem produces a condition. The condition is this: we are inside the only part of the universe, that is, from our position, the universe. The rest is real but unreachable, present but causally absent, part of the same physical totality, but not part of the same causal story. The Milky Way is small relative to what we can see, and what we can see is small relative to what exists. And what exists, all of it, in every direction, across every scale, is generating its own account of itself from its own sealed islands, and those accounts will never reach each other. The universe is not just large. It is fragmented, at the deepest level, into sealed domains of causal relevance. And each domain, if it contains the right conditions, contains the only universe its inhabitants will ever know. Ours happens to contain us. Ours happens to contain the question. Whether it contains the answer to the question of how large it really is, of what lies beyond our horizon, of whether the universe is one thing or many, and whether it has a size in any sense we can define. That is what the next descent must confront. Not the emotional weight of isolation, but the intellectual weight of convergence. The moment when all the separate threads, geometry, inflation, topology, causal horizons, the nature of size as a concept, arrive at the same place and reveal what they have in common. They have in common the observer. They have in common the fact that every measurement, every inference, every framework, every number in this documentary was produced by something embedded inside the thing being described. And that condition, the condition of being inside, changes not just what we can know, but what it is coherent to ask. The paradox is about to become exact. Pull three threads together, not to tie them off, to see what they share. The first thread, the universe's size, depends on which framework you accept, flat and infinite, topologically compact, or inflationary, and no observation from inside the observable sphere can determine which framework is correct. The denominator in the comparison the title promises is not a fixed number. It is a variable whose value depends on theory. The second thread, the event horizon, driven by dark energy, has structurally sealed most of the observable universe from causal contact with our position, and will continue sealing more of it as cosmic time advances. The accessible universe, the region with which any physical interaction is possible, is smaller than the observable universe and shrinking in content. The isolation is not contingent, it is geometric. The third thread, size, as a physically meaningful concept, requires an external perspective, a vantage point from which the measured object can be viewed as a bounded thing embedded in a larger context. The galaxy has this. The universe does not. Every measurement of the universe's size is made from inside it, and therefore measures the measurer's horizon, rather than the universe's extent. Three threads, each arrived at independently, through different routes in the descent, each pointing at something the others also point at. The question is, what that something is. What principle, if named precisely, explains why all three threads arrive at the same difficulty. The principle is this: there is no observer-independent description of the universe as a whole. Let that be stated without drama, because its implications are dramatic enough on their own. In physics, observer independence is the gold standard of reality. A measurement is considered physically real, rather than an artifact of the measuring process, when different observers, positioned differently, moving differently, using different instruments, agree on its result. The mass of an electron is observer-independent, within any given reference frame. The charge on a proton is observer-independent. The ratio of the circumference of a circle to its diameter is observer-independent. These quantities are features of reality that do not change depending on who is asking the question. They are, in the deepest sense, properties of the thing being measured, rather than properties of the relationship between the measurer and the thing. The size of the Milky Way is, within appropriate uncertainties, observer-independent. Any sufficiently advanced observer, positioned anywhere within the observable universe, using the same physics we use, would agree on approximately the same value for the galaxy's diameter. They might use different units. They might define the galaxy's edge differently. But the underlying physical fact, the extent of the gravitationally bound structure of stars, gas, and dark matter that constitutes the Milky Way, is something that any observer with access to the galaxy could measure and agree on. The size of the observable universe is not observer-independent in the same way. It depends on who is observing and from where. The observable universe is not a fixed sphere with a definite radius that any observer would agree on. It is a sphere centered on the observer, whose radius is determined by the age of the transparent universe and the expansion history of space from the observer's position. An observer in a galaxy 10 billion light-years from us has a different observable universe, centered on them, extending to 46 billion light-years from their position, overlapping with ours in some regions, and extending beyond ours in others. Their observable universe and our observable universe are not the same sphere. They are different spheres, each centered on a different observer, each sampling a different but overlapping region of the total universe. There is no frame of reference from which both spheres could be observed simultaneously as objects in a larger space. There is no cosmic viewpoint, no God's eye perspective, from which the observable universe of every possible observer could be laid out and compared the way you might lay out different countries on a globe. The observable universe is not a feature of the universe. It is a feature of the observation, a relationship between the observer's position, the age of the transparent era, and the expansion history of space. This is what the three threads share. The first thread, framework dependence of total size, is a consequence of the fact that no observer inside the universe can access the information needed to determine the universe's global geometry, because that information is beyond every observer's horizon. The second thread, causal isolation via the event horizon, is a direct expression of the observer's inability to transcend their local causal patch, because the geometry of space-time in an accelerating universe makes that patch permanent and sealed. The third thread, the inapplicability of size as a global property, follows from the fact that size requires external measurement, which requires a vantage point outside the measured object, which the universe by definition does not permit. All three threads are different expressions of the same underlying condition. The universe cannot be described from outside, because there is no outside, and the attempt to describe it as a bounded object with a fixed size is the attempt to apply a concept that requires an external perspective to a thing that has no external perspective available. This is not a limitation of current physics. It is not a gap that will be filled by a future theory of quantum gravity, or a more sensitive CMB telescope, or a deeper understanding of dark energy. It is a structural feature of the universe's relationship to observation, a feature that would be present in any universe in which the speed of light is finite, space is expanding, and observers are embedded within the system they are trying to describe. Now consider what this means for the specific comparison the title asked for. The galaxy has a size because it has an outside. You could, in principle, position yourself beyond the Milky Way's gravitational influence and observe it as a bounded object against the larger background of the cosmos. This is exactly what we do, in a sense, when we observe other galaxies. We see them from outside, as bounded structures with definite forms and extents. We cannot do this for the Milky Way only for practical reasons. Our position inside it makes the direct external view impossible, but the principle is sound. The Milky Way has an outside, and therefore it has a size in the fullest sense, a property of the object independent of any particular observer's position. The universe has no outside. The attempt to measure its size from inside, it always produces a measurement of the observer's horizon. The attempt to infer its size from theory always produces a framework-dependent answer. The attempt to define its size philosophically always requires either choosing an observer-dependent sphere or accepting that the concept doesn't cleanly apply. This is the convergence point. The comparison between galaxy and universe is a comparison between a quantity that is observer-independent and a quantity that is, at the most fundamental level, observer-dependent, or framework-dependent, or both. It is a comparison between a number and something that is not quite a number in the same sense. The ratio is real, 10 trillion to 1, within the specific framework of observable universe versus galactic disk. But that ratio is not the ratio of the galaxy to the universe. It is the ratio of the galaxy to our horizon. The horizon is real. The universe behind it is real. But the universe behind it is not the universe as measurable quantity that the ratio assumes. Here is where the specific descent of this documentary, the paradox descent, reaches its point of maximum depth. Not maximum darkness, maximum precision. The paradox was introduced at the beginning as a disruption of ordinary certainty. We started with the assumption that comparing galaxy to universe was a straightforward scale question. Two known quantities, one ratio. The descent exposed the hidden assumption in that framing, the assumption that the universe has a definite size available to be compared. The successive frameworks, flat, infinite, topologically compact, inflationary, multiversal, each attempted to provide that size, and each failed in a different way. The first by making the denominator infinite, the second by making it unknown, the third by making it dependent on physics we cannot test from inside our horizon, the fourth by dissolving the concept of a single universe into an ensemble with no total size. The convergence of the three threads, framework dependence, causal isolation, observer dependence of the concept of size, does not resolve the paradox by providing the missing number. It resolves the paradox by identifying what was wrong with the question. Or rather, not wrong but incomplete. The question, how big is the universe compared to the galaxy, is asking for a ratio between two quantities, assuming both are quantities in the same sense. The descent has shown that they are not quantities in the same sense. One is an observer-independent property of a bounded object. The other is an observer-dependent, framework-dependent, and possibly concept-transcending feature of the totality of existence. This is not a defeat for science. It is a discovery. The discovery that the question reaches a boundary. Not a boundary of knowledge in the sense of information not yet gathered, but a boundary of applicability in the sense of concepts stretched beyond the domain where they produce determinate answers. Physics has encountered this kind of boundary before. When Newton's mechanics were extended to velocities approaching the speed of light, the equations didn't simply become inaccurate. They produced contradictions, violations of causality, speeds exceeding the fundamental limit. The resolution wasn't more Newtonian mechanics. It was a recognition that Newtonian concepts, absolute simultaneity, observer-independent time, additive velocities, didn't apply in the new domain. Relativity didn't fix Newtonian mechanics. It replaced the conceptual framework in the domain where Newton's concepts broke down. When quantum mechanics was applied to the behavior of electrons in atoms, classical concepts, definite position, definite momentum, continuous trajectories, produced predictions that contradicted observation. The resolution wasn't better classical mechanics. It was the recognition that quantum objects don't have definite position and momentum simultaneously, not because we haven't measured them carefully enough, but because the concept of having both simultaneously doesn't apply to quantum objects. The limitation was not in the measurement, it was in the concept. The situation with the universe's size has the same structure. The concept of size as applied to the universe, as applied from inside it, with no external perspective, in a domain where causal horizons prevent any global measurement, may be approaching its domain of non-applicability. Not in the way that Newtonian mechanics was wrong within its domain, but in the way that asking for the weight of justice or the color of Tuesday fails, not because the answer is unknown, but because the concept and the object are not matched in the way the question assumes. The strongest responsible statement current physics can make is this: the universe has a size, the size of the observable sphere, that is real, observer-specific, and precisely measurable. Beyond that sphere, the universe almost certainly continues, and its extent is either infinite or finite and unknown, or framework-dependent, in ways that make extent a theory-laden rather than a measurement-based concept. No future observation from inside the observable sphere can determine which of these possibilities is true. The boundary of our knowledge is not a frontier where telescopes are currently pushing. It is a causal wall built into the geometry of space-time, past which no information can travel, and therefore past which no observation can reach. The exact boundary of current knowledge is not a number. It is a statement about concepts. We know the size of the galaxy. We know the size of the observable universe. We know that the universe extends beyond the observable sphere. We do not know how much further it extends, and the methods we would need to find out, observations from outside the observable sphere, are forbidden by the physics of causal horizons. We know that inflation almost certainly occurred, and almost certainly made the universe vastly larger than the observable sphere. We do not know whether inflation was eternal, and whether our observable sphere is one bubble in a multiverse, because no observation from inside the bubble can confirm or deny this. We know that the universe is flat to our best measurement precision, which is consistent with infinite extent, but flatness does not imply infinite extent and cannot determine topology. We know that size, as a concept, is cleanly applicable to bounded objects with well-defined outsides, and that the universe does not have a well-defined outside. What we do not know, what we genuinely, structurally, permanently do not know, is whether the universe has a total size in the sense that would make the comparison the title promises a real, determinate, fully meaningful answer. One final thread has remained quietly in the background. What would it actually mean for the universe to possess a size, and does that meaning belong to the universe or to the observer measuring it? The question of what it would mean for the universe to have a size, and whether the universe provides that meaning or whether we bring it with us. Size is a concept that evolved in creatures navigating a world of medium-sized objects, at medium-sized scales. You are larger than a mouse and smaller than a mountain. The rock is further away than the tree. The river is wider than the path. These are observer-independent facts about the world. Facts that any observer with functioning spatial cognition would agree on. Size, in this context, is a relation. X is larger than Y, or X has extent E in direction D, measured from a reference point. The concept assumes that objects have definite boundaries, that those boundaries are observable, and that the measurement of the distance from one boundary to another is independent of the measurer's position, within the limits of everyday experience. At galactic scales, size still works. The Milky Way has definite boundaries, definable, if somewhat fuzzy, edges where the disk's stellar density drops to negligible levels and the dark matter halo gradually merges with the intergalactic medium. The measurement of its extent is, in principle, observer-independent. Size at galactic scales is the same concept as size at everyday scales, extended to larger numbers. At the scale of the observable universe, size begins to acquire its observer dependence. The 93 billion light-year diameter is real, but it is the diameter of a specific observer's horizon, not of a bounded object in the usual sense. The concept is still applicable, but it has shifted from property of an object to property of an observer-object relationship. At the scale of the total universe, whatever lies beyond the horizon, size as a concept encounters the wall, not because large numbers are difficult to process, but because the properties the concept requires, a bounded object with an external perspective available, are not present. The universe has no boundary that can be observed from outside. It has no external perspective. It is not a bounded object in the sense that the galaxy is a bounded object. Asking for its size is asking for a measurement that the structure of the thing being measured does not permit. What the universe has, instead of a size, is a geometry, a shape, in the mathematical sense, flat, positively curved, or negatively curved, possibly a topology, simply connected, like infinite flat space, or multiply connected, like a torus, possibly a dynamics, expanding at a rate determined by its energy content, currently accelerating due to dark energy. These are real, definite, physically meaningful properties. They are what physics can actually assign to the universe as a whole. They are not a size. They do not translate into a number of light-years in the way the comparison requires. The galaxy has a size. The universe has a geometry. The comparison the title asked for is not a comparison between two sizes. It is a comparison between a size and a geometry, between a number and a structure, between a measurement and a framework. And yet the number is real. 10 trillion to 1, galaxy to observable universe. The number is true within the framework of the observable sphere, and the observable sphere is the only universe for which size is a coherent, determinate, observer-independent concept. The number is the best answer physics can provide to the question as asked, and it is simultaneously a complete answer and an incomplete one, complete within its domain of applicability. and incomplete the moment the question pushes beyond that domain. Here is what the convergence reveals, stated as precisely as the science permits. The universe is almost certainly much larger than the observable sphere. The minimum estimate, from the flatness measurement and conservative inflationary models, is a universe at least 10 to the power of 23 times the observable volume. The realistic estimate, from most inflationary models, is vastly larger than this. The theoretical maximum, eternal inflation producing an ongoing multiverse, is a universe without a total size in any well-defined sense. Within the observable sphere, the ratio of the Milky Way to the universe is approximately 10 trillion to 1 in volume. This is the most precise, honest, and physically well-grounded answer to the title's question. Beyond the observable sphere, the ratio is either infinite or unknown, and very large, or undefined, depending on which framework is correct. And the framework cannot be determined from inside the observable sphere. The boundary of current knowledge is precisely here. We know the ratio within the observable sphere with high confidence. We know that the ratio to the total universe is larger, much larger, than 10 trillion to 1. We cannot determine how much larger, and the methods that would allow us to determine this are forbidden by the causal structure of space-time. This is the deepest the descent can go without leaving physics for speculation, and it is deep enough. Deep enough to see that the question, followed honestly, does not arrive at a number. It arrives at a structure in which the measurable and the unmeasurable are separated by a horizon that is not an accident of our current technology, but a permanent feature of the physics of an expanding universe with a finite speed of light. The galaxy is on this side of the horizon. It is the platform from which all measurements are made. It is the local structure that contains the question. And the question, having descended through flat geometry and inflation and topology and causal isolation and the observer dependence of size, has arrived at the only honest resting point available. The recognition that the comparison between galaxy and universe is not a comparison between two known quantities, but a comparison between a known quantity and a concept, and that the concept, at the scale of the total universe, does not produce the determinate answer the comparison assumed. What it produces instead is a different kind of answer, not a ratio, a position, a recognition of where the observer stands relative to what can and cannot be known. Inside a galaxy, inside an observable sphere, inside a causal island that is sealed from most of the universe by the same dark energy that is slowly pulling that universe apart. The observer is here. The universe is out there, mostly unreachable, mostly unmeasurable, probably incomparably larger than the part that can be addressed. The galaxy is the platform. The observable sphere is the library. The event horizon is the wall. And the wall is not going anywhere. There is one final question the convergence produces, not a new question, but a more precise version of the one we began with. We asked, how big is the galaxy compared to the universe? The descent has revealed that this question, at full precision, becomes, what is the relationship between the only part of the universe that can be known and the rest of it that cannot? The answer to that question is not a number, it is a condition. A permanent, structural, physics-mandated condition in which the known is a small, isolated, finite island in an unknown that may be infinite, and in which the concept used to compare them, size, applies cleanly to the island and only approximately, framework dependently, and possibly not at all to the unknown beyond it. The galaxy is 100,000 light-years wide. The observable universe is 93 billion light-years wide. The total universe is either infinite or finite and far beyond those 93 billion light-years, or, if the concept is pressed hard enough, something that has a geometry rather than a size. And the most precise, honest, scientifically grounded answer to how big the galaxy is compared to the universe is this: the galaxy is everything we can stand on. The universe is everything we cannot reach. And between those two things, the platform and the horizon, the known and the sealed, is a relationship that is not a ratio and not a metaphor, but a condition of existence for any observer embedded inside an expanding universe with a finite speed of light. Come back to the sky, not the data, not the frameworks, not the event horizons and inflationary fields and topology scales and curvature parameters. The sky itself, the specific, physical, immediately present sky above a dark field somewhere far from city light, on a night when the atmosphere is stable and the moon has set and the Milky Way has risen high enough to show its full arc from one horizon to the other. You are back here, or you never left. The numbers and the frameworks were always just a way of understanding what you are actually looking at when you look up at this. At the pale river of accumulated starlight crossing the darkness overhead, thicker in some directions, thinning in others, interrupted in places by dark lanes of dust that block the light of stars behind them, fraying at its edges into individual points that your eye can just barely resolve if you look slightly away from them, using the more light-sensitive peripheral cells of your retina rather than the color-detecting central ones. You know more about what you are seeing now than you did at the beginning. That is certain. But knowing more has not made it simpler. It has made it stranger. Stranger in a way that is not unsettling in the way that ordinary strangeness is unsettling, but strange in the way that something familiar becomes when you understand it deeply enough to see that its familiarity was a surface, and beneath the surface it was always this: vast, isolated, contingent, real, and participating in a universe whose full extent it can never access, and whose total size it cannot determine. The Milky Way is still 100,000 light-years across. That number has not changed. The measurement stands. The galaxy's diameter is one of the most stable and well-grounded quantities in the entire edifice of knowledge this documentary has been building and dismantling and rebuilding. 100,000 light-years, give or take, depending on how you define the edge and which part of the structure you are measuring. The disk, the stellar halo, the dark matter halo, which extends perhaps 10 times further than the visible disk and constitutes the majority of the galaxy's mass. 100,000 light-years for the part you can see, perhaps 1,000,000 light-years for the full gravitational structure. Either way, a definite, bounded, measurable, observer-independent quantity. That stability is worth noting, because it is now surrounded by instability on every side. The galaxy's size is certain. The universe's size is not. The galaxy's extent is observer-independent. The universe's extent is either observer-dependent, framework-dependent, or concept-transcending. The galaxy has an outside. The universe does not. The galaxy is the one fixed point in a comparison whose other term keeps escaping definition. And this is the thing that the return to the opening image makes visible. The thing that the opening could not yet show, because the descent had not yet been made. The opening showed the sky. It showed the Milky Way arching overhead, and noted that you are not looking up at it, but across it, embedded within it, inside it, looking out through its disk at the universe beyond. The opening disrupted the comfortable assumption that comparing galaxy to universe was straightforward. It introduced the word observable as a splinter hidden in plain sight. Now the return to the same image carries everything the descent discovered. You are not just inside the galaxy, looking outward. You are inside the only part of the universe that is, from your position, fully causally connected to you. You are inside the island. The galaxy is part of the island, and the island is defined not by its contents but by its horizon, by the event horizon that dark energy has drawn around your causal future, and is slowly, permanently tightening. The sky above you is not a window onto the universe. It is a window onto the past, onto the light that has had time to reach you, from objects whose current state you cannot know, in a universe whose total extent you cannot measure. Look at a specific star. Any star bright enough to resolve clearly in the night sky. Let it be Betelgeuse, the red supergiant in the shoulder of Orion, approximately 700 light-years away. The light arriving at your eye from Betelgeuse left that star roughly 700 years ago. You are not seeing Betelgeuse as it is. You are seeing it as it was in the 14th century, when the Black Death was moving through Europe, and the Mongol Empire was fragmenting, and no human being had any conception of what a star actually was. A ball of plasma sustained by nuclear fusion, a structure millions of times the volume of the Sun, in the late stages of its life, and likely to end in a supernova at some point in the cosmological near future. Betelgeuse might already have gone supernova. The explosion might have happened centuries ago, and the light from that explosion might be less than 1,000 years away from arriving at Earth. Or it might not have happened yet. You have no way to know what Betelgeuse is doing right now, because right now, at 700 light-years, is not accessible to you. You are seeing its past. You will always be seeing its past. Every observation you make of every object beyond your immediate physical environment is an observation of the past, by microseconds for nearby objects, by years for nearby stars, by billions of years for the most distant galaxies your telescopes can resolve. This is not a technical limitation. It is the fundamental nature of observation at the speed of light. All knowledge of the external world arrives with a delay. The delay is usually negligible, but at cosmic scales it becomes the primary fact. The fact that structures the entire enterprise of observational astronomy, that makes cosmology a science of history rather than a science of the present. That means every map of the large-scale structure of the universe is a map of how things were arranged at different moments in the past, not of how they are arranged now. The sky is a time machine. The Milky Way, the band overhead, the disk containing the Sun and 400 billion other stars, is the part of the time machine you are physically inside. The rest of the visible universe is the part of the time machine you can observe but not touch. And beyond the edge of the observable sphere, the rest of the universe, whatever lies beyond the 46 billion light-year horizon, is the part of the time machine you cannot even observe. You are not looking at the universe. You are looking at the most recent available light from the part of the universe you happen to be inside, plus the light that has had time to reach you from progressively older epochs in progressively distant regions. That is what the night sky is. That is what all of astronomy is. A layered record of the past, with the most recent layers nearest and the oldest layers furthest. and a wall at the back where the record simply stops because the universe was opaque before that wall was formed. Now add the one thing the opening could not yet say, and that the closing can say precisely. The wall is not at the edge of the universe. It is at the edge of what you can see. The universe continues beyond the wall, almost certainly continues, in all likelihood continues by a margin so enormous that the observable sphere we have spent this entire documentary exploring is, relative to the total, less than a grain of sand relative to every beach on Earth. That margin is not guesswork. It is the minimum predicted by the physics of inflation, the framework that best explains the flatness of space and the uniformity of the CMB and the spectrum of primordial density fluctuations. Inflation did not predict a universe just large enough to explain what we observe. It predicted a universe vastly, comprehensively, almost certainly incomparably larger than what we observe. And that larger universe, the one beyond the wall, the one that cannot send us signals, and from which we cannot receive them, and to which our questions will never travel, and from which no answers will ever come, that larger universe is real. It is physically real, in the same sense that the far side of the moon was real before any spacecraft had ever photographed it. Our inability to observe it is a consequence of physics, not of the universe's failure to exist. It is there. It is not ours. The galaxy contains us. The observable universe contains the galaxy. The total universe contains the observable universe. And the total universe, the real, physical, fully existent total universe, has no size that can be stated in the way the title's question assumed. This is what the descent has arrived at, and it is worth stating one final time as a synthesis, rather than as the conclusion to an argument. The question was not wrong. The question was reaching for something real, an understanding of the galaxy's place within the cosmos, a sense of the proportion between the local and the total, a reckoning with scale as a way of reckoning with existence. Those are legitimate and important things to reach for. The descent did not show that the question was unanswerable. It showed that the question, followed honestly, leads somewhere more interesting than an answer. It leads to the recognition that the galaxy is the most stable and certain term in the comparison, the known, the measured, the observer-independent, the bounded, the real in the fullest measurable sense. And the universe is the term that cannot be fully stabilized. That depends on framework, on position, on the concept of size itself, and whether that concept applies at the scale of the total. The comparison between them is not a comparison between two numbers. It is a comparison between what can be known and what cannot, between the local and the total, between the island and the ocean beyond the horizon. And the island is not nothing. This is the thing that is easy to miss when the numbers are very large and the scale is very extreme. That the island, however small relative to what surrounds it, is the entirety of what is accessible, knowable, causally relevant, and real in the practical sense to any observer embedded within it. The Milky Way is not a negligible structure in a vast, indifferent universe. It is the structure that contains every observation ever made of the universe. It is the platform from which every measurement in this documentary was taken. It is the only place, as far as any evidence goes, from which the question of the universe's size has been asked. That the question cannot be fully answered from here is not a failure of the platform. It is a consequence of the structure of what the platform is asking about. A question asked from inside a sealed island about the size of the ocean cannot be answered by observing the island. The island is the question. The ocean is what the question is about. And the horizon between them is not a wall in the pejorative sense, not a barrier that frustrates, but a definition, the precise, physics-determined line between what the island can know and what it cannot, between the universe as it presents itself to observation and the universe as it actually is. One photon. Consider one photon. Emitted from a star in a galaxy approximately 13 billion light-years away. A galaxy forming in the early universe, when the cosmos was young and dense and blazing with the energy of rapid star formation. When the large-scale structure we now see was just beginning to condense from the nearly uniform plasma of the early universe. The photon is emitted, carries the energy of a single atomic transition in a single atom, in a single star, in a galaxy that will, over the next 13 billion years, evolve in ways neither we nor any observer in that galaxy could have predicted at the moment of its emission. The photon travels. It crosses the expanding space between its origin and our position, a journey that takes 13 billion years, during which the universe expands, cools, forms structures, produces galaxies and galaxy clusters, and the cosmic web, produces on a specific small planet, in a specific small galaxy, a species that builds instruments sensitive enough to detect single photons arriving from 13 billion years in the past. The photon arrives. It triggers a detector. It becomes data. It becomes part of an image. One pixel in a deep field photograph. One point in a spectrum. One count in a survey of the early universe's galaxy population. That photon is a message, the most ancient kind of message, a physical object crossing physical space, carrying physical information. It tells us about the star that emitted it, about the galaxy that star inhabited, about the state of the universe 13 billion years ago at the location of that galaxy. It is real information, genuine and precise. But it tells us nothing about what that galaxy is now. It tells us nothing about the 13 billion years of that galaxy's history since the photon left. It tells us nothing about whether stars still form there, whether the galaxy merged with others, whether any of its worlds ever produced observers who looked at their sky and wondered about the size of the universe. The photon is a message from the past. The present of its source is as sealed from us as if it were in another universe. And that galaxy, the one whose ancient light just arrived, is within our observable sphere. Its past is visible. Its present is not. Its future never will be. The galaxy on the other side of our event horizon, the one at 20 billion light-years, beyond the causal boundary, the one whose civilization was imagined earlier as scanning their sky for signals from us. That galaxy's past is visible too, for now. Its ancient light still arrives. But its present is already gone from our causal future, already sealed, already as permanently inaccessible as any moment before the Big Bang. We are receiving its history. We will never receive its news. This is the texture of the universe from inside the island. Not emptiness, not silence. A constant, continuous, extraordinary arrival of ancient light, photons from billions of years of cosmic history, carrying information about how the universe was, from positions distributed across a sphere 93 billion light-years in calm-moving radius. An extraordinary abundance of historical information, a permanent, structural absence of present information beyond our immediate cosmic neighborhood. A universe that reveals its past generously and guards its present absolutely. The Milky Way, your galaxy, the island you were born into, the structure that has been orbiting its own center for 10 billion years, sits inside this deluge of ancient light, this permanent present silence, this sealed-off causal future. It is 100,000 light-years across, and it contains everything you can touch, and everything your descendants could ever touch. And it is embedded in a universe so much larger than itself, that the comparison, carried to its full honest conclusion, does not produce a ratio. It produces an asymmetry between the known and the unknown, between the finite island and the unmeasurable ocean, between the place where the question is asked and the thing the question is about. The arc of the Milky Way overhead has not changed. It is still the same pale river, still the same galactic disk, seen edge-on from a position 2/3 of the way from the center, still lit by the accumulated light of hundreds of billions of stars, most of which will outlast the sun, and some of which burned out before the solar system formed. It is still enormous by every everyday measure. Still the largest structure visible to the unaided human eye. Still the home of every living thing ever confirmed to exist. But it is not large compared to the universe. It is large compared to the part of the universe we can see, and that comparison yields 10 trillion to 1 in volume, a real and staggering number. Against the total universe, the actual, fully existent, probably incomparably vast total universe. The comparison cannot be completed with a number, because the total universe does not offer itself to external measurement, does not have a size in the sense the comparison requires, and extends beyond every horizon we can define by an amount that physics suggests is enormous, and that observation cannot constrain. What the galaxy is, relative to the universe, is not small in the way a pebble is small on a beach. It is locally complete, containing everything that any observer within it can ever reach, know, measure, or affect, and globally negligible, a structure whose contribution to the universe's total extent and content is, by any reasonable estimate, so small as to be unmeasurable, even if the total were knowable. Locally complete, globally negligible, both at once, without contradiction, because local and global here are not matters of preference but of physics. The local is what the causal structure of space-time permits you to access, and the global is what exists beyond that permission, real, but permanently beyond reach. If you want a number, and the question deserves one, even knowing its limitations, here it is. The Milky Way occupies roughly 10 to the negative 35th power of the total minimum inflation universe's volume. That is 1 part in 100 billion trillion. For the most likely inflationary scenarios, the fraction is smaller still, diminishing toward 0 as the inflationary expansion factor increases. In an infinite universe, the fraction is exactly 0. In any scenario consistent with current observations, the fraction is so small that expressing it numerically does not communicate meaning. The number is too extreme for any analogy to bridge the gap between the figure and its physical reality. And yet the galaxy is not 0. The galaxy is not nothing. The galaxy is the place where the fraction was calculated, where the number was derived, where the observations were made, where the frameworks were built and tested and compared, and found to be incomplete. The galaxy is the place from which the asymmetry between local and global was discovered. If there is anything in the universe, any physical process, anywhere, that could be described as the universe becoming aware of its own scale, it happened here, in this galaxy, on this planet. in the minds of organisms that evolved to navigate a savanna and somehow ended up measuring the curvature of space. That is not a comfort designed to soften the impact of the numbers. It is a fact, a physical fact, as precise and as real as the numbers themselves. The universe did not develop a means of measuring itself everywhere simultaneously. It developed it here, in this galaxy, from this island, looking outward through this sealed causal bubble at the ancient light arriving from its own past. The question this documentary was built around, how big is the galaxy compared to the universe, has led somewhere that the question could not have anticipated when it was first asked. It has led to the recognition that the comparison is real and limited and honest and incomplete all at once. Real because the numbers within the observable sphere are genuine and important. Limited because the observable sphere is not the universe. Honest because the limitations are not hidden. They are built into the physics and stated plainly. Incomplete because the universe's true extent remains, and will remain, beyond the reach of any observation from inside the island. There is one question that arises from all of this. Not a new question introduced at the end, but the question that the descent has been approaching since the opening image. The question that the original title was really asking, beneath the request for a ratio. If the universe is almost certainly incomparably larger than anything we can observe, and if our galaxy is an almost unmeasurably small fraction of the total, and if the concept of size applied to the universe as a whole becomes framework-dependent, and possibly inapplicable at the largest scales, then what is it that we are actually part of? Not what is it that contains us. That question has been answered as well as it can be. The observable universe. Probably a far larger total universe, possibly an eternal multiverse. In any case, something vastly beyond the galaxy. But what are we part of? What is the nature of our membership in something that extends so far beyond our access that the extension cannot be measured, cannot be observed, cannot even be assigned a definite size? That question does not have a scientific answer, and it would be dishonest to pretend otherwise. Physics can tell you the size of the observable sphere, the geometry of space, the expansion history of the universe, the minimum size implied by inflation, the causal structure imposed by dark energy. Physics cannot tell you what it means to be a part of something so much larger than you can know. That question lives at the boundary between physics and philosophy, between measurement and meaning, between the observable and the merely real. But it is the right question. It is the question that follows from the science without being answerable by the science. And the fact that it is not answerable does not make it unanswerable forever. It makes it the question that the next generation of thought, and the generation after that, will carry into whatever understanding comes next. Before that, one image to end on. Not a metaphor, a fact. Somewhere beyond the observable horizon, at a distance we cannot measure, in a direction we cannot specify, in a region of the universe that shares our Big Bang and our fundamental physics, but lies permanently beyond our causal reach. A star is emitting light right now. That light is traveling outward in all directions, including in the direction of our position. It will never reach us. The expansion of space between that star and our position is carrying the space itself away from us faster than the light can cross it. The photons are moving. The distance is growing faster than the photons can travel. The light will never arrive. That star does not know this. It is simply burning, fusing hydrogen to helium, radiating energy across the spectrum, illuminating whatever orbits it, in whatever system it inhabits. Its light is real. Its photons are real. Its existence is real. And its light, aimed in our direction, will travel forever toward us and never get here. The universe contains that light. The universe contains the question of whether we will ever find a way to know that it exists. If size is what you can reach, then the universe that matters to us, the universe of our causal history and our causal future, the universe in which everything that has ever happened and everything that ever will happen from our position is contained, is not 93 billion light-years across. It is exactly as large as the light that can find us.